Now it's pouring down raining.
Okay. Now, let me get the share screen. Okay, chapter 15. There we are. Let's expand it. Now, I think some people are trying to get in, so let me get back. In fact, I'll get back to this later. Okay. Now, okay. Okay. Got to go back to where we were in chapter 15. Okay, heliocentric model. Okay. All right, can y'all see my slide, or at least part of it?
Yes.
Okay.
Yes, sir.
All right. I think we're ready to go. Now, Leon, I'm not sure I had you here before, so let me get you here now.
I think Caitlin's trying to come in.
Oh, really? Again? Okay. See, it's not showing. Let's see, where is Caitlin? Try this again. I don't see her. Is she already in here? Let me see.
I see her. It's just saying connecting to audio, but.
Yeah.
All right, Caitlin. Yeah. She's in the class. She just hasn't connected the audio yet.
Okay.
Okay. Let me go through who I've got here, and you tell me if you don't hear your name. I've got Don here, Capri here. I don't have Bridget. Is Bridget here? I have Nakia. I don't have Thomas. Is Thomas here? I have Juan. I don't have Scott Lucas. Is he here? Okay. I don't have Haley Mason. She hasn't been here from the beginning. I've got Patrick. I've got Caitlin. I don't have Parisha. Is Parisha here today?
She was here earlier, I thought.
Well, if it was, let me see. I don't see her now. Let me look and see if I can find Parisha. Hold on.
Did he call my name, Capri?
Who's that?
Capri?
Okay, Capri, I've got you.
Okay.
I'm looking for Parisha. It sounds like it, but it's not the same. Okay. Parisha I don't have. I have Harry. I have Cormisha. I don't have Rod. Is Rod here? I don't have Jacob. Is Jacob here? I don't have Anthony Tremaine Weston. He hasn't been here from the beginning. I've got David Whitlock. I don't know if he's back yet. And I just saw that Leon had come in. Okay, and I had Roy and Valerie. So I don't see anybody else waiting. So I'm going to close this out because it's blocking the screen. Okay, now folks, sorry if you were here or not here before. We were getting ready to start class. I was getting things lined up, and suddenly my audio went out. I could see everybody, but I couldn't hear anybody, and my microphone obviously wasn't working. And I tried, and this has happened before, and everything I tried, nothing works unless I turn it all down. Turn everything off, turn off the computer, and bring it back up. And every time I've done this, every time it stopped audio in the middle of a recording, here's what I found out. Microsoft is trying to load a update. Those just aggravate the fool out of me. That should not interfere with anything that we're doing here, and yet it seems like every time that's happening. Okay, I'll just let Cormisha back in. So I don't know if that's what it is, but every time it's happened, they've been trying to do an update. So that's the only thing I can figure is going on. So here's what we're going to do, folks. I'm going to try to move this taskbar out of the way because it keeps blocking. And another thing that happened, I think I got in a hurry when I was trying to bring it up the second time, and I think I forgot to let it reconnect to the internet. And I think that was my fault that time, so I had to take everything down again. Okay, now the question I had for you earlier, and this is about where we left off before, is this where you had that we left off last time? I remember talking about Mars wandering across the sky like this. Is this where you remembered? Anybody? Okay. I'm hoping this is where we were. Did we get everything covered on this slide? I think we did. Copernicus came up with this idea that the sun is now the center of the solar system. He may have said universe, but it was at least the solar system. And Kepler's laws would further explain the heliocentric model. I don't think we had gotten to Kepler's laws yet. Had we? The inconsistencies that were found in the geocentric model, for instance, the planets wandering across the sky with no fixed order and stuff, this was explained when you took out of the Earth being the center and put the sun in the center, the Earth going around the sun, Mars going around the sun, then everything made sense. So Kepler's laws would then further explain the heliocentric model, and that's where we're going now, is Kepler's laws. I think we're going there if I can get the PowerPoint to advance. Okay. That's the end of the slideshow. I can't believe it.
Okay.
Purples come in disguise sometimes.
Mr. Fowler, so why has the sun been setting a little bit towards the north?
Okay, say that one. Oh, why does the sun look like it moves from east to west?
Why has the sun been setting further north than it usually does?
Okay, that's an excellent question. I'm glad you noticed that. Okay, here's why. We're going to talk about this in the very lab today, but we're going to hit it now. I wish when we were in class, I had a globe and I could show it to you. The Earth tilts just slightly, okay? So when we move around the sun, sometimes the Earth is pointing toward the sun and sometimes the Earth is pointing away from the sun. And that's what makes our seasons. This would be our winter season. This would be spring season. This would be summer season. And this back here would be fall season. Okay, we're right here getting close to what they call the summer solstice. And what you noticed, I hope, was that the sun every day gets a little bit higher in the sky. Okay, a little bit higher every day. And the reason for that is we're tilted toward the sun. Right now we're leaving spring and coming to summer. In fact, just in a week or two, we'll be in summer. And that's when the sun is going to be at the very highest. And after that, then the sun starts dropping again. Okay? And the reason they call it solstice, that means sol, S-O-L, means sun, and stis means still. The sun stays still. Because here the sun looked like it was here. And then every day as we move, the sun goes up a little bit and then stops. And then once June 21st happens, it starts dropping again. The reason for that is that tilt of the Earth as we go around the sun. So that is exactly what's happening. We're going around the sun, but a little bit of an angle. You'll be hitting this a lot. 23.5 degrees. 45 would be like this. 23.5 is like this. So I was exaggerating some. This is our tilt. And with that tilt, that's why the sun seems to be moving up in the sky And after June 21st, it'll start dropping in the sky, ever so slightly. And what you were mentioning, I noticed our house, in fact, I'm facing due north right now. And every morning when I get up, or every night when I go to bed, I close all the blinds in the rooms that have blinds. And then in the morning, I go back and open them up. And in the summertime, the sun, even facing due north, I see sun coming in the windows. So that's what you mean. The sun is moving to the north. In the wintertime, that'll never happen. You'll never have that sun coming in the northern window. Not directly. I mean, sunlight comes in, but the direct ray of the sun will not come in the wintertime. And then it'll keep getting here earlier every day until June 21st, and then it starts retreating again. So you're absolutely right. The sun does appear to be moving north of due east, and it'll set north of due west every day until next, around September 21st. That's when the fall or autumnal equinox happens. And equinox means equal night, equal day and night, 12 hours daylight, 12 hours darkness. So that's exactly, I'm glad you noticed that. That's what's happening. And that's because we're going around the sun, but we're at an angle. Our axis has a tilt to it. And that's what makes, in the summertime, the sun's highest in the sky and actually rises north of east and sets north of west. You're absolutely right on the money there. Okay, now I can't believe this is the last slide, and yet it says so. So let's pick up and go from here on Kepler's 3 laws of motion. Now I'm not going into great detail, I'm just going to tell them to you. They're in your book, and if you've got your book open, it's on page 400 if you got one of these great big old heavy books. If you've got one of the smaller books, those are, the page is probably 15-23. 15-23, meaning chapter 15, the 23rd page of chapter 15. So Kepler had 3 laws of motion. The first of these, and these are planetary motion, not to be confused with Newton's law of motion. These are Kepler's 3 laws of planetary motion. Okay, the first law states that each planet moves in an orbit around the sun. That's what we've been talking about. Now, this orbit you see here for Earth and for Mars, they aren't quite accurate because these look like they're perfect circles, and they're not perfect circles. They are slightly elliptical, meaning one place it's going to bulge out a little bit and another place it'll come in a little bit. Slightly elliptical. Now, here's the difference between an ellipse and a circle. A circle has a single center. Everything goes around at the same distance from that center. An ellipse has 2 places they're called foci. Focus, F-O-C-U-S, plural is foci, F-O-C-I. The sun's at the center of one of those. So that means the Earth is a little bit further from the sun at some times, a little bit closer to the sun at others. Not much at all, but that's, yeah.
Is that called like grand solar maximum and minimum?
That, if you're talking about the size of the sun, yeah, that's what makes the sun look a little bit bigger sometimes of the year, a little bit smaller at other times. But it's a very, very, very small difference. So I'm not sure that you'll notice it, but astronomers will notice it and can measure it. But that's Kepler's first law. States that each planet moves in an orbit that has the shape of an ellipse. Think of, it's not quite an egg shape, but it's kind of like that. It's an oval shape, okay? An oval shape, but the sun is not in the center of that. It's on one of the foci, and it's not far from being circular, but it's just slightly, okay? So there's the first one. The sun is at one focus. The second law, Kepler's second law, states that an imaginary line between the sun and a planet moves over equal areas of the ellipse during equal time intervals. Now that's a little bizarre. And I'm going to show you their illustration of this. And this is a gross exaggeration, but they're doing it to illustrate what's going on. Now, you might not be able to hear me when I hold it up. But this is on page 400, and you see that figure right there. You see the big triangle. I can't get
We
my
can't
finger.
hear you. I'm sorry.
Okay. If I hold the book up, it blocks the camera. It blocks the microphone. Can you hear me now? At all? Can you hear me now?
Now we can hear you.
Okay. Can you see that figure, the little pink? I wish I had more fingers. Okay. Right there. Okay. When we're close to the sun. Now, this is a greatly exaggerated ellipse. You see, we're closer to the sun here, much further there. But in the same time period, you travel that big little segment there as you do that skinny little segment there. But because it's so long, the areas are the same. Now, they don't look like they are, but they are. And again, this is grossly exaggerated, but that's what it's talking about. And yes.
So is when the sun appears to be bigger,
Yeah.
in his law is it going to be hotter on Earth?
Okay. Now that's another excellent question, and on average, yes. But for us in the northern hemisphere, no. And here's why. When we are closest to the sun is almost our dead winter. It's around January the 4th. We're in the coldest part. Why are we coldest? Because we're pointing away from the sun. That tilt that we have. And when we're farthest away from the sun, that means at that time, we're pointing toward the sun. That's around July 11th or something like that is when we're closest to the sun. No, farthest from the sun. But we're pointing toward the sun, so that's our hottest part of the year. Now, who has it bad then are people in the southern hemisphere, like Australia. Australia, when we're closest to the sun, they're pointing toward the sun, okay? So their summer is exaggerated in heat, and their winter is exaggerated in cool. The thing is, it's such a small difference in distance that it really doesn't contribute that much. The tilt of the Earth contributes way more than how close we are, because the difference is very small. In the next chapter, which we'll get to today, I think, if we can keep Zoom working, that will explain that a little bit better, perhaps. But yeah, these are excellent questions. You're looking ahead to some very real things. Now, what does that mean for here again, I'm going to try to hold this, for the sun to be covering the equal size here as the imaginary line between us and the sun, equal area swept. Well, that means we're moving much faster here and slower there, okay? The reason for that is the further you are from the sun, the more you slow down. The closer you are, you whip around. It's kind of like, this just shows how old I am. There was a game we used to play on the playground. We didn't have that many things to do. It was called Crack the Whip. Have any of you ever done that? You get a long line of people, everybody's holding hand, and the person in front then takes a sharp turn, and the person at the end almost is thrown out. Have any of you ever water skied? No? When you're water skiing, I'm terrible at it, but I've only done it a few times, and I'm terrible. But when you get too slack on it, you're going real slow. When you let it get way out there, you're really flying. Well, it's the opposite of that around the sun. When you're real close to the sun's gravitational pull is pulling you real fast past it. And when you're way further away, and you're not that much further away, you slow down a little bit. That's what those comets were doing. Remember we talked about this? When they come around the sun, they're really whipping. And when they're way out there in the Oort cloud or in the Kuiper belt, they're moving really slowly. And that's why it takes them 70 to 100 to 200 or more years for them to make a complete revolution around the sun. They're in really elliptical orbits. Ours are really close to circular to slightly elliptic. But there's Kepler's second law, that an imaginary line between the planet and the sun cuts the same area in an equal time period. The third law states that, and this is a bizarre one, it states that the square of the period, that's how long it takes to go around the sun one time, that's the period, go around the sun one time. For us, it's exactly 1 year, 365 and a quarter days. That's our period. So the square of the period of a planet's orbit is proportional to the cube of the planet's semi-major axis. What? Okay, don't worry about that one, except for this. Remember how the planets, nothing seemed to fit? When you use Kepler's law and plot the planets, look at the graph then. Now this is what they call a log-log graph. That means you have a logarithmic scale on the vertical axis and on the horizontal axis, and notice how every planet fits right in place. So these that are way, way, way far away, on a log scale, they don't seem that far. And they all seem to be not exactly equally placed, but very close to it. And guess what belongs in between Mars and Jupiter? The asteroid belt, which they think should have been a planet, but they think bully Jupiter and its strong gravitational field kept that planet in between there from ever coagulating and becoming a regular planet. So if you're seeing that on page 401, that's what that's representing. Now they have a couple of examples here, and we won't go into because it's using the concepts that you did back in chapter 2. We didn't do chapter 2. We started in chapter 14, so really there's no reason to do that. But you can read through, and if you can follow what they're doing, you see that indeed that makes sense. And we really are right at the end of the chapter now. Okay? There's a blurb in the text on Gerard Peter Kuiper, the guy who the Kuiper belt of comets was named after.
We can't hear you, I'm sorry.
Okay. I'll try to hold it up and talk over it, but it's hard to do. There is the blurb in the book on Gerard Peter Kuiper, and he's the one that the Kuiper belt of comets is named after. And notice here he was a Dutch born. He was born in the Netherlands, Holland, but he grew up and did his work in the U.S. So he was a U.S. astronomer, born in the Netherlands, but he grew up here. He completed his education in his own country, immigrated to the U.S. in 1933. Does anyone know what was happening in 1933? You don't remember that? No, I'm just kidding.
Recovery.
Say again?
Recovering from the Great Depression.
Okay, you're absolutely right. That was right around the Great Depression. And it was also about the time that Hitler was coming into power in Germany. And those two, one of those two probably chased Kuiper out of the Netherlands and into the U.S. He later became a U.S. citizen, and he did all of his major work here in the U.S. Now, I don't know, nothing is ever said that he was Jewish, so it may be he just didn't want to be around when Hitler was there, or the depression that was hitting Europe, also was in the U.S., but we were probably coming out better than Europe was. So I don't know why, but anyway, that was what was happening at that time. Great little article on him. But remember, this article in the book cannot be your source for your research paper. You can use him as your research paper, but you have to find your sources outside the book. Okay? And if you read this, you'll see he's not the only one mentioned here. And by the way, he discovered the second moon on Neptune. I mean, there's just all sorts of things that he did. Pretty incredible stuff. And any of those things he discovered would be a legitimate paper topic. So you can go with that. And that pretty much ends chapter 15. Does anyone have any specific questions on 15? All right. I'll go over just like I did at the end of chapter 14. Nothing replaces reading the chapter. So I hope you have books, ebooks, some sort of book, PDF, some sort of book, but read it first. And then at the end of the chapter, you'll see there's a summary. I'll try to talk under it. Okay. There's a summary. It's a fairly decent sized summary. Goes on to the next page as well. And after that, there's a series of terms, key terms. There they are. I just can't show them, and it's in your book on page 403, the key terms. It's a fairly long list of key terms. A good sized summary, fairly long list of key terms. But then after that is applying the concepts. Now these are multiple choice questions. Okay. They start right there, all of the next column, and on to the next page. That's 403 and page 404 and on to 405. These are all applying the concepts. To me, that's the best thing to study for your test. Because most of your test is going to be just like you saw with the first test. I think all those questions were multiple choice. Maybe not all on the second test, but most of them will be. And so there's 41 questions here. That's probably a few fewer questions than most of the chapters will have, but still a good number. Your test is going to be probably between 15 and 20. Okay? So there's a lot more covered here. None of these will be exactly the same questions on your test, but they're covering a lot of the same material. So these are great things to study. And the good news is the answers are given. I can't see. Where are they? I think that's where the answers. Oh, there they are. There's the answers. Okay. So if you try to read the questions, quiz yourself, check the answers. If you can't get that answer and can't figure out why, then ask that in class next time. Then after that, there's questions for thought. There's 19 of those. That's probably a few more than most chapters have. Then you have 6 for further analysis. That's about normal. And then the parallel exercises are a lot like the examples in the text. Most of those we aren't doing because they depend on stuff from the first half of the book we didn't have. All right. Now, I meant to do this earlier, and then our Zoom went down, all that mess happened. What we're going to do today is stop a little bit earlier than before. Boo hiss. I know y'all don't want to do that. We normally, the class ends at 6:15. Normally we stop at, 4:45? No. Yeah, 4:45, and that's when we start the lab. Today we're going to stop at 4:15 and do the lab. Because we didn't do a lab last time, we're going to do it this time, but we're going to take a full 2 hours to do the lab. And unfortunately, it'll probably take us most of those 2 hours. I don't know if y'all saw it on Blackboard, did you? Lab 2?
Yes.
Okay.
I'm looking now and I can't see it.
Okay, it's under the messages, Blackboard messages. That little thing, icon that looks like an envelope.
what if I'm on the app and I'm not able to access a laptop at the moment?
Okay. Well, okay. I don't know what to do in that case. If your laptop's not working at all, or just the sound and stuff.
No, sir. I'm looking at class on my phone. My whole laptop screen cracked. Like I can't see nothing on it.
Okay.
I've been doing work on my phone now.
Okay. But is your laptop working? It may not be working on Zoom, but can you open things on your laptop at all?
No, sir. I cannot see
not at all.
nothing on my laptop.
Okay. Well, I have no way of sending it to you except for that way, and even if I sent you by email, you can't access email either, right?
Yes, sir. On my phone, I can.
Oh,
I got the app on
yeah,
my
but
phone.
okay. But it's hard to see a lab on the phone, isn't it? I mean, I don't know. How big's your screen? I mean, okay. So on Blackboard, can you see what's in Blackboard on your phone?
Yes, sir. I can see due dates, everything.
Okay. So when you go to Blackboard and you have a strip across the top that has a lot of icons on it. One of them looks like a piece of paper, and that's your grade book. The next one, or somewhere over there, is one that looks like an envelope. That's the messages. If you go to that one that looks like an envelope, click on it, you'll see I've sent you 3 things so far. One was Lab 1, one was Test 1, and the latest thing I sent you was Test 2. Lab 2. And when you open Lab 2, it'll say PHS111 L2, Lab 2. When you open that, this one's a big one. I think it's like something like 7 pages. And unfortunately, whoever was holding the iPad, that would be me, wasn't quite holding it as well as he should have been. And some of the pages are a little scattered, but now I can't figure this one out. I put every page down exactly the same, took a picture of every page, and when it came out on the thing, the last 3 pages are turned sideways. Okay? So what you're going to have to do is be able to, at some point, print that lab. Now what you can do before then, if you can see it on your cell phone or wherever. Now we're not going to do the lab now. We're going to do it at, 4:15. So let me know when 4:15 gets here. Okay, it's 30 minutes away. Okay, at 4:15, we're going to stop in chapter 16 and start the lab. And at that point, it would be good to have it printed off, but if you don't have it printed off, have your piece of paper, and hopefully you can see it in your phone, and when you see what it's doing, you write down what goes in those blanks. And later, when you can print it off, then fill in the blanks, okay? Or at least you'll know how to fill in the blanks. So I'll explain that more when we get there. We're not there yet. Let's go on and get started in chapter 16. Okay.
You are recording, right?
I am recording, yeah. Now, I've only been recording for 33 minutes because the first recording, we didn't have any new material on it, and I had to shut it down, and it was going to end it. So rather than having, it was something like maybe 15 or 20 minutes of me calling roll and, fussing about the system not working right and, that kind of stuff. But so I just started over, and we've been going for 33 minutes on the new recording. All right, so what I'm going to do is continue in this slideshow, okay, and at the same time pick up the next one. I know the screen sharing has stopped. I'm going to pick up a new share. Okay. Chapter 16, here it is. All right. Can y'all see the beginnings of 16 yet?
Yes.
All right. So let's go from current slide. All right. Chapter 14 was the whole universe. Chapter 15 was the solar system. Chapter 16 is the Earth-Moon system. So it's entitled Earth in Space, but we're also going to talk, maybe not half the time, but part of the time about the moon. So it's really the Earth-Moon system. Okay? The core concept here, which you'll find, and by the way, I'm going to move, you can't see this, but it's in my way. I'm going to move this taskbar down to the bottom because it's in my way. Okay, the core concept, which is found on page 407, which in your book will be 16, if you have a little book, 16-1. Okay, the first page in chapter 16, the Earth in space. The way that the Earth moves in space is used to define time, describe location on the surface, and causes other recurrent phenomena. And we already answered in somebody's question today why the seasons occur. Phenomena such as that. Okay, now here's another sort of artist rendition of the solar system here. Now this is a little bit better than the others in the fact that the planets are all lined up, which they wouldn't be, but this is still showing most of the planets over here in one area, and that's usually not the case. So my guess right now is that's probably Mercury, that's probably Venus, this is Earth, that's probably Mars, probably looking at Jupiter here, Saturn here, and there's Uranus and Neptune way out there. Their sizes are not correct, their distances are not correct, their orientation's not correct, but it's just another way. And this good old sun over here, but remember the sun is more than 700 times bigger than all these others, everything else put together. So obviously the scale is not right, but it gives you an idea of what we're talking about. We're now going to be focusing on the Earth here, and maybe this isn't the Jupiter, this may be our moon, that you're on the moon looking back at the Earth. If so, the scale is probably still not right. But anyway, let's go from there. Well, I can't advance the slide until I click on it and then it advances. Okay, so let's start with the shape and the size of the Earth. Okay, now the Earth is very close to what they call an oblate spheroid. What does that mean? Well, a sphere is a perfectly circular, solid shape. Okay? In other words, everything on the surface of the sphere is exactly the same distance from the center of the sphere. That's a sphere. So what's a spheroid? It's something very similar to a sphere, but not quite. An oblate spheroid means it's a bit big in the middle. In other words, it's a little bit larger around the equator and slightly, as they say down here, pear-shaped, not apple-shaped. Okay, now that's an exaggeration on the pear-shaped. Okay, so here's a deviation. We're slightly pear-shaped. We sort of are a little bit bigger in the southern hemisphere than we are in the northern hemisphere. Not much. And this makes no sense to me at all. They say there's a lump in the Pacific. Well, wait a minute. The Pacific's an ocean, and if there was a lump in it, the water would go downhill, it seems like. So that doesn't seem to make sense. And then the second one, they say there's a depression in the Indian Ocean. Well, it seems like if there's a depression in the ocean, all the water would flow into it. So they're meaning something slightly different from literal lumps and literal depressions, I hope. I don't understand. They don't go into great detail about it, but it basically means we're not a perfect sphere. We have some irregularities. Now, how much or how little are these irregularities? Very, very minor. So the elevations and depressions of these deviations are less than 85 meters. Now, 85 meters is fairly close to between 90 and 95 yards. So it's not even an entire football field. And when you picture how incredibly massive the Earth is, to have the total deviations between a perfect spheroid to be less than 85 meters, less than one football field, that's nothing. That is almost nothing. They're there, but they're not major. Not major at all. Now, don't go by this picture, okay? This picture was on one's fairly close to it. This is not the distorted Earth. This is the Earth. The sun is over here, remember? The sun's over here. This part of the Earth you can't see because it's in the shadow of the sun. It's down here. This looks like a perfect sphere. It's not quite, but this is not the deviation. This is just the part that's in the shadow of the sun. You can't see it. You cannot see that. So what are we looking at here? It's hard to tell. Most of the Earth is covered with water, and I'm trying to figure out what this is. This looks like maybe the west coast of Mexico. That looks like the Baja Peninsula south of California. This is part of Mexico. This would be the U.S. west coast here. And somewhere over here would then be the Gulf of Mexico, but you can't see things very well. So I'm just making a guess at that. Okay? Now this is a gross exaggeration. Okay? This is what a perfect sphere would be like, the dotted circle here, and that is a circle. Whereas an oblate spheroid is, like I said, a little fatter around the equator and a little less fat at the poles. Okay? And now, this isn't quite matching what these numbers are here, but it's relatively close. The difference between the maximum here and the minimum here is only about 42 kilometers. But these aren't elevation depressions. This is how much wider we are at the equator than we are at the poles. And that's only, like it says here, about 42 kilometers. Now, a kilometer is 1,000 meters. Okay, so it's a good bit. 42 kilometers would be about. Was someone trying to just come in? I didn't see. Oh, I can't see. I seem to have lost Zoom. Are y'all seeing what I'm seeing? Can you hear me?
Yes, sir.
Okay, you can see shape and size of the Earth?
Yes.
Okay. My entire Zoom taskbar has disappeared on me, so I couldn't tell if I was still on Zoom or not. Something popped up and then disappeared. But as long as you can see this, that's what's important. Okay, so that 42 kilometers out of a total of 12,000 kilometers, that's not very much. This is a gross exaggeration of the difference. In terms of miles, that's 26 miles as opposed to 8,000 miles. So what is 26 compared to 8,000? Almost nothing. Almost nothing. Okay. So we're not much out of spherical, but we are slightly out of spherical. All right. Now, this gets to what the question was earlier about why things look different at this time of year. Now, there's a figure in the book which is really, it's more like the space objects in perspective. See, I can't see my picture anymore, so I can't tell if I'm in the camera. Can you see that drawing? Okay. This is on page 409, if you got the book. You'll see there the 4 terrestrial planets are tiny. These are the rocky planets. The first one there would be Mercury. It's the smallest. Then Venus and Earth are almost the same size. Then Mars looks even smaller than Mercury. It's not. It's just that Mars is closer. But you see that big old thing behind all of them? That's Jupiter. And that's a good relative illustration of how much bigger Jupiter is than the 4 terrestrial planets. I mean, it's huge. Then Saturn is behind Jupiter, and then Uranus and Neptune follow behind them. All of the gas giants are way, way bigger than those 4 terrestrial planets. I don't know if you can see.
Professor Fowler,
Yes.
Capricia is trying to get in.
Oh, is she? Well, see, that's the problem. I've lost my taskbar. So let me see if I can do anything. I can. Let me see what escaping does here. Okay, you probably lost your PowerPoint. I'm going to minimize
No,
it.
we can still see it.
Okay, here we go. I don't know why that disappeared, but now I've got to bring it back up. Chapter 16. Okay, is that coming back to you now?
We never lost it. It's still there.
Okay, you still got motions of the earth?
Yes, sir.
Okay, good. All right. So this is what the, I can't remember who it was asking early on, where in the world, why things look different now. Now, there's another illustration on page 409 I sort of want to talk about, but it's hard to do right now because we haven't really discussed it much. But remember when I said the plane of the ecliptic? The ecliptic is basically the path that the sun seems to take across the sky, but of course, the sun's in the center and all the planets are in that plane. So when you look at the plane that the sun's on, that also reveals the that center part of the solar system. Okay, and on this one you'll see there's Jupiter. No, there's Saturn just off the ecliptic. I can't read all these because it's such bad lighting. Mars is right off the ecliptic. Jupiter's right off the ecliptic, and Mercury's right off the ecliptic. This just happened to be one time of year when all of those were on the ecliptic, and this seems to be the fall months around September. We're not in that time now. We're more over there, Mercury and Jupiter. And remember, when we saw that Lab 1 stuff, that was what we're on. Okay, so motions of the Earth is 16.2. Okay. 3 of the Earth's motions are independent of the motion of the sun or the galaxy. And this is the 3. Okay? Our yearly rotation around the sun. It takes us 1 year to go all the way around the sun. Okay? It takes us 24 hours to spin one time on our axis. And, now this third one is bizarre. Those others, 365 days and a quarter, 24 hours, those are fairly quick. The next one says the clockwise wobble of the Earth around its rotation axis. Okay? That is anything but rapid. That takes tens of thousands of years for it to make one little wobble. We haven't even been in existence. Mankind has not been in existence long enough to experience one wobble of the rotation axis. But they know it's happening. Okay? Now, we'll talk about that more a little bit later, probably next time. Okay? Here are 7 motions of the Earth through space. These are called the conspicuous motions. Now, 3 of these we just mentioned. But now these other 4 have to do with the sun and the galaxy. Those other 3 did not. So here's the other. First, the daily rotation of the Earth. One time around in 24 hours. The spinning of that. Now, that spin at the equator, if you're at the equator, you don't realize this, but you're going 1,670 kilometers per hour. Now, that would be about equivalent to 900 miles per hour. I'm just making a rough guess there. About 900 miles per hour. That's how fast at the equator the Earth is spinning. You don't realize that because we're so big, we don't sense that. You think we're still and everything else moving around us. No, that's how fast we're moving. Because we're a big planet. Not nearly as big as Jupiter, but we're a big planet. Okay, number 2. The monthly rotation about the Earth-Moon center of mass. That we never notice, okay? But what that means, and we'll talk about more of that at the end of the chapter, so let's just hold on to that one for a while, okay? But in 1 month, when the moon, okay, A year is defined by how long it takes the Earth to go around the sun. A day is defined by how long it takes the Earth to spin one time around its axis. How a month is defined, now this is approximately. Month comes from the word moon, M-O-O-N and M-O-N-T-H, month and moon. The moon goes through one cycle of its phases, we'll talk about this later, in a month. Usually in any given month, you have one full moon, one half moon, well actually two half moons, one's the first quarter, one's the last quarter, one new moon. It happens every month, okay? Every now and then you'll have two of one of those, one at the beginning of a month, one at the end, but those are on the longer months, okay? So, the moon is going around the Earth one time a month, basically. And as it does, it pulls the Earth. The moon is going like this around the Earth, but the Earth's doing like this in the middle. And the reason is the moon has a significant gravitational field. So it makes us move a little bit just as it's moving. So it moves a lot, we move a little. That's what it means, the monthly rotation about the Earth's moon center of mass. Okay? The yearly rotation around the sun, that's the one we talked about before. That takes about 365 and a quarter day approximately. Now, the orbit of our solar system, the whole solar system, about the center of the Milky Way. Oh, wait, sorry, back up. Our moving around the sun, that's about 106,000 kilometers per hour. That's how fast we're going around the sun. Now, we don't ever sense that. We don't feel that because that's a long trip. It doesn't seem like we're going that fast, but we really are. That would be about 60 to 70,000 miles an hour. Okay, that's how fast we're going. We're going around the sun. Okay, now the orbit of our solar system, the entire solar system around the center of the Milky Way, it's about 370,000 kilometers per hour. Okay, but let's see, in terms of miles per hour, about 200,000 miles per hour. Goodness gracious, we're flying through space, but we don't feel it, we don't sense it. Okay, the orbital motion within the sun's local star group. So we're going around the Milky Way, but you see we're also sort of revolving around each other in that local star group. Now that one's really moving about 1 million kilometers an hour. That'd be about 600,000 miles an hour. Okay. Then the motion of the Milky Way galaxy relative to remote galaxies, well, we're only going 580 kilometers per hour, which would be about 350,000 miles per hour. Yo. Now, here are the minor motions. These are very slow compared to the others. The change in shape and size of the Earth's orbit. Remember, we're not quite circular, we're slightly elliptical, meaning when we're closer to the sun, we move just a little faster, and when we're further from the sun, it's just a little slower. Not enough to notice. And then the one we talked about last slide, that slight, very slight change of tilt of our axis that takes tens of thousands of years for us to do one change. And then, here's one that we don't realize. Our rotation rate is slowing ever so slightly. I mean, just very minor change. We haven't been able to detect it all the time we've been on Earth. They just know it's happening in a longer term. Okay? And now they'll use this illustration again later, but I'm going to use it now. This shows how old I am. Do any of you ever remember playing with a top? You wind the spring around the top and you throw it and it spins like crazy. And it stands almost perfectly straight up and spins really fast. Okay?
Vaguely.
Someone does remember that. Thank you.
I do.
Okay. Now, you know that a top, after a while, will slow down and spin, and when it slows down its spin, it begins to wobble. Okay? Now, go back to that wobble of the Earth's thing. That's like the wobbling of a top. Not quite as much, but like that. And the slowing of the spin, we are slowing down very, very slightly over time. All right. So those are the motions of the Earth. How are we doing on time?
But I do have a question. So
Surely.
since we're slowing down very slowly, is it a possibility that something's going on with the core of the Earth? Is it going to ever get like a jump start to where it's going to rotate back again? Or
Now, there is something going on with the Earth in its magnetic field right now.
Okay, all of you are hitting some great points here. Now, number one, let's go back.
It's affected by the core itself. So, like, does that mean, is it the core? Is something wrong with the core that's making it slow down, or like the movement within the Earth?
Okay, I think you're right on the money. And here's what, and this is more my guess than not knowledge. It's just sort of a guess. Our outside the core, we're solid. The outer part of the core is liquid. Okay? So the outer part of the core, that's what's spinning at the rate we're seeing here. The yearly, daily rotation. That's this right here. Now the liquid that's in the middle, it's not turning that fast. It's sort of like my wife likes to put up preserves in the summertime. We've done 2 batches of strawberry preserves. We're looking forward to doing some peach preserves later. We may do some. We've done some plum before. If we can find them, we're going to do it. Now, I say she likes to put them up, but she likes to get me to stir them because she gets tired of standing there over that hot thing stirring. So I wind up being the stirrer. Now I can turn the spoon like this, but the liquid doesn't go as fast as the spoon. Right in the spoon it does, but the rest of it just sort of lags. So you're right. The center part, which is molten liquid, doesn't turn as fast as the outer part. And there's friction between those two. That friction may be, and this is a guess, may be what's slowing it down just a little bit. It's not enough to notice, okay? We're talking about over billions of years, it's slowed just a little bit. So it's nothing that we're going to notice in our lifetime. Nothing that they're going to notice between when man first showed up, which was not that long ago, and when man finally disappears, which probably isn't going to be all that long either. You know, we wipe ourselves out or something. I don't think any of us will ever notice that it really has slowed down any. But they can tell it is slowing slightly. And I think the reason is the friction between the liquid inner core and the solid, but it's not a smooth transition there. It's jagged inside there. So I think there's some friction. That's just a guess. Now, somebody said this change in the magnetic field is going on.
Right, the magnetic North Pole. Why is it shifting towards Siberia?
Okay. We're going to talk about that in 2 different places. I can't remember if one of them's in this chapter and one of them's in a later chapter. I know one of them's in a later chapter. I believe it's in this one too. And I don't know why. I have never been able to figure out why it's happening, but they know that it's happening.
And it all of a sudden it continues to multiply its speed.
Okay, there's no all of a sudden involved. It's all so very gradual, we don't know. But it's a gradual shift. And actually, this is the part that I find absolutely impossible to explain. I can sort of make a guess, but I can't explain it. About once every 22,000 years, I believe it is. I may have the number wrong, but I believe that's about it. The Earth's gravitational field actually changes. But it's not a sudden change. it's gradually changing over those 22,000 years. So right now, like you said, it's moving from northern Canada and moving more toward northern Siberia. And at some point, our gravitational field is probably almost going to act like it disappears, but then at some other time, it's going to pick up and be pointing in the other direction and get stronger and stronger and stronger. Now,
and it's weird because if you look at the movement of it in the past and how fast it started moving recently in the past like 30 years, it kind of sped up once it got over, I guess it was like land and hit like an ice field or something.
okay. Now, that's interesting, and it sounds like that would almost be a fantastic paper topic if you're really interested in it. If you can find enough to write on it, that really sounds interesting. Here's my layman's terrible example of what I think is going on. Everything pretty much that happens movement-wise follows what we call a sinusoidal curve. I mean, if you think about it, number of daylights and darkness. We're longer days now. It's going to keep getting longer. Then they're going to start getting shorter. They get shorter and then shorter and shorter, and then they get longer again. It follows a sinusoidal curve. So my guess is what's happening with the Earth's magnetic field. We're at a time where it's sort of rapidly changing, in a geologic sense, rapidly changing, not in anything that we'll notice, but it is going to change. And at other times, it will change much more slowly. So you'll hardly notice any change at all. And it's kind of like what one of the earlier questions, the Earth, right now, you can see the sun going up in the sky a little more every day. I don't know if you'll notice. I can't notice it, but it does. And it's going up so slowly now you can hardly tell. At some point, it will stop and then slowly start coming down again. That's, as you're close to those times, you can't notice any change. But later you'll see, oh yeah, I can tell a difference there. And so the changes are so incredibly slow. Like I said, you might say it seems like it's speeding up now from what it used to be, but it's still going awfully slowly. Okay, if you can find enough information for a paper topic, that sounds like a great one. So, but if you're more interested in something else, go with that. Okay, I want you to go where your interest is. Okay, now the overall picture. Okay. Oh man, we're supposed to stop at 4:15, aren't we? You let me go over a minute. Okay.
Oh, I'm sorry.
No. Excellent questions, by the way. We'll pick up here with this slide that says overall. I've got to find it here in the book. Let me see. The previous slide said 7 conspicuous motions.
Earth motion in space continued. Is that the one we're supposed to start?
Okay. I can't find the specific slide here. Let me see if I can find it. Well, y'all just help me remember. Okay, let me see. We may start here. Let's just start with motions of the Earth. And we'll say we already covered the first of this. We'll pick up from there and go. Because otherwise it's going to be hard to find an exact slide for it. Okay. So we'll begin on page 410 next time, right at the first of 410. Okay, let me get my sheets in place here. And what we're going to do now is go to the lab. I don't know if any of you were able to print off your labs. If you have, fantastic. If you haven't, not going to hurt you, but it's going to be harder to do the lab. Let me get out of the slide set here. It's going to take me just a moment or two to do so. And we've stopped screen sharing, but I'm going to pick up something else in just a minute. And I think
Dr. Fowler, you are still recording, right?
Okay, yeah, I'm still recording. We're a little over an hour into it, an hour and 5 minutes almost. What I'm trying to do is find. I had to shut everything down before, so I'm having to bring it all back up again. I'm going to show you the lab, and this will also be our worksheet. So if you can replicate it as well as you can, lab 2, there it is. And again, whoever was holding the camera was doing a lousy job of it. Okay, let me get, where did Zoom go? I don't know. Okay, here we are again. So let me get the slideshow pulled up here. Well, I don't see it. Let me go back and find it again. Okay, there's the lab. There it's open. Okay, I'm just going to minimize it. Minimize this. Okay. Well, let's try it this way. Okay, can you see that? It's, well, it says computer, USB.
Yes.
Okay, you can see that. Okay, I'm going to try to open this. Can you see that now? Experiment 48, motions of the sun.
No, it's black.
That's black. Why is that black?
It's like we have half of your screen. We can see half of your.
You can see the part over. Can you
Yes.
see this part over here? The one that says 233 kilobytes.
Yes.
Okay, you can see that, but you can't see
half of it. No, not the full screen.
Okay, this is so bizarre. Okay, does that get any better?
That's why it's called a computer.
I know. Is this the whole thing black now, or can you see motions of the sun?
Still half.
It's all black.
Half and half.
It's still half and half. Okay, let's try this. Is it still half and half?
There.
You got it.
All right, amazing. Okay, now I got to get you people out of the way. Juan's right in the way, of course. All right. So here's motions of the sun. Now we didn't do experiment 47. I thought about doing it last time, but I really could not figure any way to make it work in a virtual environment. But this one, I hope we can. Okay. So, all right. What we're going to be talking about here, let's picture what we've got going on. Remember that first lab when we had the star map. And remember that little square in the middle of the star map, and that was the center directly overhead called our zenith. Remember that? Remember? It's a little crosshair. Okay, that was our zenith. That was directly overhead. Now let's imagine I'm going to face due north. And believe it or not, I'm almost facing due north right now. If I face due north and take an imaginary line that goes from due north on the horizon and go directly overhead to my zenith, and then directly behind me to due south, that is what we call our celestial meridian. Okay? That's my celestial meridian. That's the point from due north to due south directly overhead. Now, when the sun, the transit of the sun crosses that celestial meridian, my celestial meridian, right here where I'm standing or sitting, that defines due noon. That's the highest point the sun will ever be in the sky today. It's already passed it for today. Okay? That's when it crosses there. It rises in the east. Rises in the east, goes over that, and sets in the west. That point is noon. Okay? That's our fundamental reference for time. Now, the interval from one noon to the next noon is what we call one solar day. That's one day based on the sun crossing our meridian, our local meridian. Okay? Now, a lot of the rest of this first page is just blah, blah, blah. So I'm not going to go over that in great detail, but I do want to point out a couple things. Remember, when it crosses that, it's called the transit across our meridian. So if it's before the meridian, over here on the east, that's called anti-meridian. Anti meaning before the meridian. That's where we get the term AM. The morning hours between midnight and noon are AM. And then after it crosses the meridian, that's post-meridian, after the meridian, and that's PM. That's where we get. So that's where the terms AM and PM come from. Anti-meridian, meaning before the meridian, post-meridian, after it crosses the meridian. Okay? Don't know if y'all realized that before. Okay, a lot of the rest of this I found is just blah, blah, blah. So let's move on past this if I can find my cursor. Okay, here it is. You can read this to your heart's content. It's fun. It's interesting. Okay, here's one thing. They mention a sundial here. I just saw it, but I can't see it now. But anyway, oh yeah, sundials are common. We're going to talk about different kinds of sundials later. We'll get to that later. Don't sweat it now. Okay. Now, what we're going to do in this lab, this is on the second page of the lab. And by the way, let me say this. To save yourself some effort and save me some effort, when you go to send the lab in to me, only print out the pages that you wrote something on. Like that first page, you read about it, we didn't write a single thing. On this page, I don't think you're going to write a single thing. But you need to read it, okay? So what's the difference in a solar day and a sidereal day? Well, solar day, the term SOL, that means sun. That is a day from the sun crossing one meridian to the next day when it crosses the meridian again. Sidereal, on the other hand, refers to stars. So that's a sidereal day. If at night you knew where your local meridian was, of course, the North Star is always going to be right in the same place on it, so it never crosses. But you pick any other star, and when it crosses your local meridian from one day to the next, that would be a sidereal day. And guess what? They're not quite the same. Okay? Not quite the same. And we're going to get into it, why it's not the same. Okay? And that's where we're going to now. Again, please read this. It's well worth a read. Okay? Now, there's talking about, they're throwing some terms out here that I'll actually throw them too. They talk about equinox, and I think they probably mention, I don't know if they mention solstices. I mentioned those as well. Let me go over again what an equinox is. Okay? Here's a word right here, so you'll see what I'm talking about. Equinox. Equa means exactly what it sounds like, equal. Nox means night, means equal day and night. The vernal equinox is the one that happens in the springtime. In the springtime, near March 21st, you're going to have equal number of daylight hours and darkness hours, almost exactly. Again in September, around September 21st, you have what they call the autumnal equinox. Again, same number of daylight and darkness. Right now, you know, there are way more hours of daylight than there are of darkness. Okay? And then the wintertime, way more hours of of darkness than there is daylight. Now here we're getting to our first calculation. The sun moves 360 degrees around the ecliptic. In other words, if you picture our globe there and the sun moving around until it comes back around, that's 360 degrees to go all the way around. Okay, now that's, okay, wait, let me back off. That's the sun around the ecliptic, not around in a day. That's the sun, let's say today is June the 8th, okay? The sun is at its highest point, okay? It's here today. Tomorrow it's going to be a little bit further because different things are happening. And it goes around, and in a whole year, it comes back around until next June the 8th, it's going to be right in the same place again. That defines that, remember that dotted circle we saw on the star map? I think I showed it to you in a couple of other places. That's the ecliptic. You know, the planets are always near the ecliptic because we're all in the same plane. Okay? So the sun moves around the ecliptic, 360 degrees around the ecliptic in 365 days because that's 1 year. So it moves almost 1 degree every day is where it moves around the ecliptic. Therefore, the sun is about 1 degree east of vernal equinox the day after vernal equinox, okay? So calculate how long you would have to wait until, now, this is going to be a little hard to do sitting here. I'm going to scroll on down. If you had it printed off, you'd see it. But I'm going to scroll on down to what they're talking about right here. Okay? Now, here's the problem, folks. Okay. On the spring equinox, the vernal equinox, the ecliptic and the equator cross right there. This is the sun's path, and there is the celestial equator. That's where the sun is, directly over the celestial equator that day. Now, the next day around, you know, now it's a day we're talking about, the next day, the sun would cross this local celestial meridian 1 day later. The trouble is, the sun has moved a little bit. It moved 1 degree further here because now after vernal equinox, the sun is a little above the celestial equator, not on the celestial equator above. And the reason for that is we spin, but we're also moving around the sun. Okay? So by the time, let's see if we can get the next figure. It may show it a little bit better. Yeah. Okay. See, this is on the vernal equinox. Okay? The sun, 12 hours of daylight, 12 hours of darkness, everything's even. Okay. We spin around once, and we're right here. But the sun's not directly overhead there. It has to move. We have to move just a little further for the sun to cross our local meridian. The reason is we're not just spinning, we're also moving around the sun. And that's 1 degree more that we move. That's what we're talking about now. Because the sun won't cross our local meridian, because we've moved a little further, we have to wait for it to go 1 more degree. That's why a solar day is just a little bit longer than a sidereal day. Because the stars aren't moving at all. We're not moving around the stars, we're moving around the sun. The stars are fixed in place. Okay? So that's what we're getting at. So let's go back here. Because we're moving around the sun at the same time we're spinning, that's what leads us to this calculation. Now this will be the first page you turn in. Okay? It says calculate how long you have to wait after the situation depicted in 48.1b from 48.1a, okay, till the sun is on your meridian. Okay? Now, I can't write on this screen, but I can write on another screen. So I'm going to go to that screen and do my writing. Okay? And that's the whiteboard. And this is really pathetic, folks. Okay? Because I have to use my finger on my keypad, and that's what I'm writing on. So what we have is 1 degree is how far we travel in a day. So that would be 1 degree in 1 day. Okay, that's what we're starting with. The D stands for day. It's not very pretty. Okay, well, what is a degree? There are 24 hours. Okay, there's 360 degrees. That's how far we spin 360 degrees in 24 hours. Okay, I hope I'm doing this right. H will stand for hours. I don't want to spell it out or put the abbreviation. Okay, if you got a calculator, take your calculator and find your, well, I've got my phone, so I have to find the calculator mode, and go to the calculator and then do 360 divided by 24. Okay.
15.
15, exactly. Now that's 15 degrees you move in an hour. Okay? So let me write this again. That's the same. These are equivalent. It probably shouldn't be equal signs, but they're equivalent. So that would be 15 degrees in 1 hour, right? You just divide it. Okay, 1 hour divided both by 24. Okay, now an hour is 60 minutes, right? So that would be 15 degrees in 60 minutes. Because an hour is 60 minutes, right? Now that M doesn't stand for meters, it stands for minutes. I just don't want to spell it out. Well, let's divide 60 by 15. And what do we get?
0.25.
No, 60 divided by 15. Don't do the top divided by the bottom divided by the
You
top.
get 4.
It's what?
You should get 4.
Yeah.
It will be exactly 4. 4 minutes for it to move 1 degree. So that ratio would be, and divide this by 15 and you get 1 degree. Divide 60 minutes by 15 and you get 4 minutes. Now that M stands for minutes, not for meters. So if you take this, basically put your units in there correctly and do it on your page here, that's how you did it. Calculate how long you'd have to wait for the situation, 1 degree, it to move 1 degree, that would be, express your answer in minutes, 4 minutes. Okay. So what does that mean? You've described one way of showing that a solar day is a little bit longer, about 4 minutes longer than a sidereal day. Okay. Now, they're next going to do it from a heliocentric model, and that's the one we've already talked about. Okay. I went back to show you that on the other. Okay. Now, the second question they have here, and you see there's some blank here, but if you read it, they never get to ask a question. It says figure 48.3, and I'll show it to you in a minute, depicts the sun's apparent motion along the ecliptic, okay, where the zodiacal constellations, I think Valerie pointed this out time, were found in the heliocentric perspective as the Earth orbits around the sun, blah, blah, blah. For example, the diagram shows the sun in Leo. A month later, it will be so that Virgo lies in the sun. Do you see a question there? They forgot to ask the question, and I don't have a clue for what their question was. So don't worry about number 2. It doesn't have a question, so it doesn't have an answer. Here's what it's referring to. Whatever month this is, the Earth is here and the sun is in Leo. And Leo kind of does look like a lion if you connect the dots, but without connecting the dots, it just looks like a bunch of stars to me. And then later, when the Earth moves from here to here, the sun will be in Virgo. That's what they're trying to say, but I can't for the life of me figure out what question they were going to ask. Okay, and it goes on around like this because the Earth goes around the sun like this, so each of these constellations go at a different. So Sagittarius, I think, is late December, early January. Okay, so you can just go on around. No question, no answer. Okay. For those who are interested in how they came up with those, this is how they came up with the zodiacal sign. So here's part A, and this is going to be most of the rest of the lab. The analemma. Now, analemma is one name for a sundial. Now, this isn't the sundial that casts a shadow on a clock face. That's a different kind. This is another kind of sundial. Okay? Now, here's what would happen if we could do it. If we were in a classroom at noon every day of the year, and that classroom happened to be facing a south wall, okay? So we had a window in that wall, and we covered that window with black plastic and just cut a tiny little circle in the black plastic. And every day, exactly when the sun was crossing our local meridian, you'd have to determine that, when it was crossing our local meridian, at precisely that time, the sun would cast a little dot on the floor, a little bit bigger maybe, or about the size of that hole that we cut in the plastic. And if every day at noon we put a dot on the floor exactly where the sun's shadow was that day, and then did that every day of the year for an entire year, you would map out a flat bottom figure 8. That's what they're talking about here. And that's the next figure I'm going to show you. That is what we call the analemma. It's a closed curve resembling a flat-bottomed figure 8, and I'll show it to you now. There it is. There is the analemma. Now, I can't show you the whole thing on this, but when you print out your lab, you'll see the whole thing on one piece of paper. Okay? Now, I want to point out a couple of things to you. This has 2 axes. This axis over here is the declination of the sun. That's how far the sun is north or south of the equator at any given day. And guess what? On September the 21st, the sun is right on the equator. It's not north or south. On March 21st, the sun is right on the equator. It's not north or south. Remember, those were the equinoxes. Spring equinox, fall equinox. Somewhere around the 21st of March, somewhere around the 21st of September. Not exactly, but pretty close. So in the summer months, the sun is north of the equator, and in the winter months, the sun is south of the equator. See, here's September, October, November, December, they're all around until you get to March, then April, then May, June, July, August, September, back again. So the northern part is when the sun is north of the equator. That's the skinny part of the figure 8. And in the winter months, the sun is south of the equator. And that's the fat part of the analemma, the figure 8. Now, you may be asking why some is fat and some is thin. Remember, we said the sun is moving around, the earth is moving around the sun a little bit. We're closer to the sun in January, so the spread there, we're moving faster, so it gets spread out there. In July, we're a little bit further from the sun, so we're moving more slowly, so the figure 8 gets scrunched together at the top. That's why the figure 8 has its shape. So the vertical axis here is the declination of the sun, how far the sun is above the celestial equator on any given day. Okay. The horizontal axis, especially at the top up here, is given in minutes. And these are minutes, and we'll talk about this later, down over the 14, 15, 16 minutes this way, over here 16, 17, 18 minutes this way. Okay? If you go to the bottom of the scale, I'm trying to remember if they have anything there. I don't think so, but maybe they do. Let me see. Yeah, these are actually degrees. How many degrees it is, east or west, okay? And again, if you think about it, every degree is around 4 minutes. 4 times 4 is 16. 4 times 4 is 16. We're right around 16 minutes one way or another, and that's what the top was showing. Now, the other scale that's on here is actually on the analemma, and those are the days of the months. Here's February, the 15th right there, the 16th there, the 17th there, the 18th there, the 19th there, the 20th there, 21st, 22nd, 23rd, 24th, 25th. So you see every change of color is one day. So there's actually 3 scales here. Declination, how many degrees above or below the celestial equator the sun is. How many minutes or degrees it is east or west of noon, by the way. That's what, let's see if it says that on the, yeah. The center axis, the vertical axis here is clock noon. So these are either minutes before or after clock noon. We'll talk about which one they are later. Okay? Now, the other scale is the days that are listed on the analemma itself. The days of the month. And here is May. Here's May 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20th. See, because the earth is moving more slowly, because it's further from the sun, that it doesn't move as far in a day. So that's why it's skinnier at the top. So you have all these things on the analemma. All right. Now that gets to, and we're going to be coming back to this again and again and again. If you had it printed off, you don't have to wait for me to move it. Okay. So now here's the page that went sideways, and I don't know why. So I'm going to have to read it sideways here. I don't know if there's anything all that important to read on this one. But once you get it, you can turn it over and read it. I don't see anything all that special here, except it does talk about when you're closest to the sun, the perihelion, that's on or about the perihelion is January the 3rd, and the aphelion is July the 7th. Okay, I was guessing 11th, but somewhere in there. Okay, those are the. Let's go back to the analemma. I want to point something out to you. What's the maximum angle that the sun makes north of the equator? And this is on June 20, near 21st. That's the summer solstice. The summer solstice is 23.5 degrees. That's it right there. What did I say the tilt of the Earth's axis is? 23.5 degrees. How about the winter solstice down here when the sun is dark more than it's light? That's really close to the 21st of December. That's the very minimum down here. 23.5 degrees south of the celestial equator. There's that 23.5 over and over again. That's as far as the sun gets north and south of the celestial equator, because that's the tilt of the Earth. That's that 23.5 degrees tilt. Okay. Now, all right. The next page is the next one that you'll have to fill in something. And unfortunately, it's not very good. Okay. Here's the first thing you do. Here's question number 3. Remember, question number 1, the answer was 4 minutes. Question number 2, there was no question, so there was no answer. Here's question number 3. Briefly describe the effect of the shape of the analemma, that's that fat 8, okay, flat-bottomed 8, if the ecliptic equator angle were to increase slightly. I think is what the rest of that says. So, yeah, were to increase. Well, what would happen? That would stretch the figure 8 north to south. Because if that angle were to increase, it would go beyond 23.5. It would go to 24 or 25, north and south, so it would stretch the figure 8. So there's the answer to number 3. Stretch the figure 8 north to south. Okay? Everybody got that one? All right.
Yes, sir.
All right. Here's number 4. Obtain from your instructor the latitude of your location and fill it in below. Well, unfortunately, we're all at different locations, but we're not far off. So since we all would have been, if we had met this summer, we'd be in Bessemer, Alabama, because I usually teach on the Bessemer campus. And I've looked it up before, and I'll tell you right now so you can fill this in wherever you want to fill it in. 33 degrees, this is our latitude. 33 degrees, 23 minutes, 45 seconds. 33 degrees, 23 minutes, 45 seconds, north. That's our latitude. I'll say it again. 33 degrees, 23 minutes, 45 seconds, north. That's how far we are above the equator, the angle distance above the equator, Bessemer, Alabama is. You may be slightly off from that, but not going to be more than a few degrees. Okay?
Can you repeat that one more time? I'm sorry.
33 degrees, 23 minutes, 45 seconds. That's the first part of the answer to number 4. Okay? Now the second part of that answer, determine the altitude over the southern horizon of the intersection, okay, of the celestial equator and the, I'm sorry, I can't get this all on one page, and the celestial meridian, your local celestial meridian. Okay, I'm going to go back to the drawing board, the whiteboard, and I'm going to try to show you that here. Okay, so it says determine the altitude over the southern horizon of the intersection of the celestial equator and the local celestial meridian. Okay, so I'm going to go back to the whiteboard and show you what they're talking about there. Okay, I'm going to clear this out of the way. Hopefully you got it now, right? Now, this is going to be awful, people. This is going to be awful. I'll say it now, but it's going to be terrible. Okay, what I'm going to have to do is draw a little globe down here. A little description of the Earth. And this is terrible. That's supposed to be a sphere. I can draw it much better by hand than I can with this. We're standing right here, let's just assume, in Bessemer, Alabama. Okay, here we stand in Bessemer, Alabama. Okay, that's supposed to be at the, ooh, you have a weird looking head, don't you? Okay, now what did I say? Here is where we are in Bessemer, Alabama, and that angle here is about, this is the equator right here. That's supposed to be an E. It didn't draw very well. That's your equator. And this angle right here is supposed to be 33 degrees 23 minutes, and for minute I'm just going to put a tick mark, a single tick, and 45 seconds.
North.
And a second mark is a double tick, like feet and inches only is minutes and seconds. Okay, now here is, now I'm going to try to improve this a little bit. Oh, why didn't I do that? Let me erase, now that I remembered I can do this, let me erase this ugly globe here, okay? I forgot. I can draw a circle. I can't draw it, but I'm going to let it draw it, okay? Ooh, I messed that up a little, didn't I?
Arrow up. There you go.
Okay, that's not too bad of a circle, is it? Okay, I'm going to erase everything else I did too. I'm sorry, I forgot I could do that. Okay. There was your ugly stick man. Oh, I shouldn't have erased that. Sorry. Okay. Now, I'm going to attempt to draw to the center of the circle. Does that look almost close enough?
Perfect. Yeah.
Okay. Now I'm going to try to draw the equator. I'm not fitting quite right. And this is the, okay, now I'm going to draw, go back to a drawing here. I don't know. I'm going to try to draw my stick man here. This is going to be pretty pathetic. There's one leg. There's another leg. There's, whoops. This is why this is hard to do. This is the body. Here's an, oops, don't do that. Okay, here's an arm. There's an arm. And let's go back and draw a little head. Y'all are having fun with this, aren't you?
Yes.
You're laughing at me, I can tell. Okay, there's his little head. Okay, now I'll go back and do my angle here. And this angle, and by the way, this is the equator here. Okay, and this angle here, say again?
Do we need to have this drawing as our answer as well, or
you don't have to draw this, but you might want to do a better job than I am, or just understand what's going on here.
Okay.
My writing is terrible. Okay. That's supposed to be a 5. Okay. Now, directly above, okay. All right. I'm going to get my line back again. Okay. I'm going to try to draw my horizon. Okay, there's the horizon. This is the north horizon. Oops. So this is pointing due north. and this is south over here. Oh, where did that come from? Okay, this is south over here. Evidently, my whiteboard only goes so far, and I went off of it. Okay, I wonder if any of you can think of what. No, I've got to get back to my line again. Directly above me. What is the line, the point directly above me called? Does anyone remember?
Zenith?
Zenith! Perfect! That's not directly above me, is it?
The north?
Okay. I need to do something else here. I need to move this out of the way. I think Valerie's in the way again. You know how she is. I think I'll move Valerie over here. Y'all can't see that I did that. Ooh, that's not right either. Okay. Now, okay. There's my zenith up here. Quit that. Okay, I've got too many things on top of each other. Okay, I made a bad choice there. There's my zenith, directly overhead. Here is my celestial meridian. Oh, this is going to be terrible. Wait, let me try to draw it as a circle. Okay. This is not going to be good, but let me try it. No, I can't do that. That won't work. Sorry. Good try, but it won't work. Okay. So now I'm going to have to go back to the drawing board, so to speak. I'm going to have to try to draw it freehand. Okay. So here it comes up here. This is my celestial meridian. It goes through my zenith. That's supposed to be a smooth, beautiful curve. It's not, obviously. Okay. And then it comes back. Oh, that's awful. Coming back here to due north. That's supposed to be my celestial meridian. Okay. Now, my zenith is here. That means 33 degrees here. 33 degrees, 23 minutes, and whoops, I forgot. Okay. This is pretty terrible, folks. I'm sorry. Okay. Let's just say that's 33. Okay. There's my zenith. This is my attempt to draw
I'm sorry, I had a brief intermission with my child having an issue. Could you go over that last section for a moment? I'm sorry.
Okay. All right. This
After you drew your celestial meridian.
Okay. So what I'm doing, the zenith is here. I tried to draw the same 33 degrees, 23 minutes, and 45 seconds here that you see from where I'm standing to the equator. That's my latitude.
Okay.
That now is where celestial equator is. CE, the celestial equator, is 33 degrees, blah, 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 beneath my zenith. Just like I'm standing on the surface of the earth, 33. Okay, so there's it. Now, let's go back to, and this is where I've messed up here, I think. I can't find my cursor. There it is. Okay. Okay. I got this in the way. I'll need to move it somewhere else. I'll move it up here. Okay. Now, let's go back to our paper. Here it is. Okay, what did it say here?
Determine the altitude over the
Yeah.
southern horizon
Yeah.
of the intersection of the celestial equator and the local celestial meridian.
And that's what I just drew. My celestial meridian was that semicircle, and where the celestial equator went, I labeled it celestial equator, that's it. So it says determine the altitude of that over the southern horizon. That's what we're asking for. So let's go back here and see if we can determine that. Okay, we know this is 33 degrees here. Here's the southern horizon here. So what is the altitude of the celestial equator? Well,
it just went out.
that would be this angle right here is a 90-degree angle. So you do 90 degrees minus this, and you get the angle that's in here. Now, I've drawn that a little too big, but I'm going to try to do that. Now, I'm going to show you the shortcut for doing these, okay? Rather than doing 90 degrees, I'm going to do 89 degrees. And 59 minutes. And 60 seconds. Because 60 seconds makes how many minutes?
1.
And that would make this 60 minutes, and 60 minutes makes 1 degree.
1
so that
degree.
would be 90 degrees. Only I've written it in minutes and seconds. So now I'm going to subtract from that 33 degrees. I'll leave off my degree symbol. 23 minutes. I'll put in that one because that's easy to draw. And 45 seconds. I wish I could leave off the 5 because I can't draw that very easily. And that's not too bad to draw. I'm going to subtract that, and what do you get? That's 56 degrees. I'll leave off the degree symbol. 36 minutes, right? And I'll draw that one in. 15 seconds. You see that? 56 degrees, 36 minutes, and 15 seconds. That's what you fill in here, right here. Determine the altitude over the southern horizon of the intersection of the celestial equator and your local celestial meridian. It's 56 degrees, 26 minutes, 15 seconds. Was that it? It's on the whiteboard. Okay. Now, question number 4 here. 5. That was 4. Use the analemma that we saw earlier and your answer we just did to fill in the table 48.1. Okay? Now, we're going to do it first for our noon altitude of the sun at our location. We're going to do this set of going to start with declination of the sun at these 4 days. February 15th, June 21st, October 15th, and December 22nd. The declination of the sun. Well, where do we get that? Right off the analemma. Did someone write down those dates? Someone jot them down real quickly.
Get them real quick.
I got it.
Okay, wait, whoa. February 15th, June 21st, October 15th, and December 22nd. Okay, let's go back here to the analemma. Whoa, what's the first one?
February the 15th.
February the 15th.
Mm-hmm.
Okay, here's February, and there's the 15th. You see it?
Uh-huh.
Okay, you go across that line.
13 degrees.
That sounds about right. 13 degrees, right on the nose. 13 degrees south. 13 degrees south. So write that in, if you got it printed on your table, 13 degrees south. Okay? That's the declination of the sun on February the 15th. Let's do the other one while we're here.
June 21st.
What 21st?
June 21st.
June 21st. Okay, we've got to go up in the upper part of the analemma. I know where that. Whoa! What did Valerie do then? She just messed up everything, didn't she?
I'm sorry.
Where is it now?
August, June 21st.
Yeah, but I can't find my.
Just a few minutes
It'll be
ago,
23 and a half.
my phone did the same thing. It had blacked out, and it was connecting me back while you was going degrees.
Okay.
Ooh.
Let me.
We see your timer now.
What's that?
We see your timer now. It's kind of blurred, but we see it.
Oh, you do?
Yes.
Yeah, there's a.
1 hour, 56 minutes, and
Yeah.
5 seconds. 21. Oh, God. It's killing me. 22nd.
Okay. June 21st?
Yes, sir.
All right. You should have been able to tell me this one. What is the declination of the sun?
23 and a half degrees.
23 and a half degrees north. Yeah, why were we even looking? Okay. All right. What's the next date?
October 15th.
October 15th. Got to go back to the southern part. Find October somewhere here. There's October. Oh, and there's the 15th, isn't it?
Okay, we can't see your map, though.
You can't.
No, we just see the timer.
Oh, wait.
Yeah, extra large too.
Yeah, really large. Like huge.
Can you see
there
that?
You are. Okay,
Okay.
now we see it.
Okay. October the 15th. Declination of the sun.
8 degrees.
8 degrees south. 8 degrees south. Get that written down. And that last date was December something, wasn't it?
22nd.
22nd. That's awful close to something you should know too. This is the flat part down here. That's right around
19. No, I'm looking at the wrong thing. I'm sorry.
right there at 23 and a half degrees south.
23 and a half degrees.
Exactly, because that's right near the winter solstice, when the sun stands still in the wintertime, as it's been dropping, and then finally starts going up again. So this is your winter solstice. Okay. So 23 and a half degrees south. All right, we got those done. Here. Those were declinations of the sun on those 4 dates. Was that January? No. Is that
February
right? Yeah. Oh, February the 15th.
June 21st.
June 21st.
October 15th.
October 15th. And
December 22nd.
December 22nd. Okay, now what we have to do, and you've got those measurements. You've written them down, right?
Mm-hmm.
Okay, so let's go back to our, and now this is moved up in the way, but it's okay. Go back to our whiteboard. Okay, remember, here's the celestial equator. What's that first date?
February the 15th.
Okay, and what was the declination of the sun?
13 degrees south.
South is the celestial equator. Here's the celestial equator. 13 degrees south would be somewhere about like I'm guessing something about like this. This is just Whoa, I thought I had a line. Where's my line?
I don't know.
Okay, this thing does this every now and then. It quits doing what it's supposed to. Uh-oh, I think I just messed it up then. Okay, I'm going to have to freehand it. Okay, it's something like this. This angle in here is, what angle you say, 13 degrees?
Yes.
13 degrees south of the celestial equator. Well, it was asking for what's the noon altitude of the sun. Well, the noon altitude of the sun at the celestial equator was here, so subtract 13 degrees from that, and you get 43 degrees, 36 minutes, and 15 seconds. Do you see that? If this...
Okay, because we're basing it off of our location.
You're facing it off the what the altitude of the celestial equator is. We already determined that 56 degrees, 36 minutes, and 15 seconds. And we just found out from our table that the declination of the sun was 13 degrees south of that, or below that, so more toward the southern horizon. So you subtract 13 from this number here, and you get 43 degrees, 36 minutes, and 15 seconds. You see that?
Mm-hmm.
Okay, so you write that down for our location. Okay, what's the next one? The next
23 and a half degrees.
north. Okay, so this was 33 degrees in here, 23 and a half degrees, and I wish upon a star. Okay, let me try something else here. Let me leave the whiteboard and go back to the whiteboard. No, it's not working.
Mr. Fowler.
Yes.
Mr. Fowler, did you say write down 43 for our location?
Say that one more time. Oh no. The altitude of the sun on, what was that date? February the 15th?
Excuse me, yes, sir.
Okay, you see on the sheet, you have February 15th, declination of the sun was 13 degrees south, and then from our location, subtract that from 56, and that gives you 43 degrees, 36 minutes, 15 seconds. That's the altitude of the sun on the 15th of February. So the next column over on the row with, okay, let me go back and show you. Yeah, right here. Okay.
Degrees and what?
Okay. On February 15th, you put declination of the sun was 13 degrees south, right?
Okay, I got it, yes.
Okay. The noon altitude of the sun at that location on the 15th of February was 13 degrees below what this one was right up here, the celestial equator, right? So 13 from 56 is 43 degrees. That's what goes here. 43 degrees, 26 minutes, is that it? And 15 seconds. That's what goes there. Okay. Now we go to, is it June 21st?
Yes.
Okay, at June 21st, we go back to our whiteboard. Ah, we've got it back again. I was hoping it would come back. But I can't get my straight line back again. So this is going to be 23 degrees north, 23 and a half degrees north. So that's going to be something like here, and this is supposed to be a straight line. It's not. So you're 23 and a half degrees north. So now this time I'm going to take the 23, 30, and we're going to add it. Not subtract it, add it, because now you're north. This is where the sun is. This is the sun at noon on, see, there's the sun. And this is at noon on, what was that, 15?
Okay, your cursor's gone, so I have no clue where you mentioned where the sun is.
Okay, you don't see my little sun there? You don't see 15 February? I'm writing it in now. Oh, that's ugly. You don't see what I've just written here?
Okay, my Zoom pictures were covering it. I couldn't see.
Okay.
Okay.
All right. Now we've gone up to June the 21st. The sun's way up there. I can't draw it in there because it's way up there. So we're asking what the altitude is here above the southern horizon. Well, the southern horizon we know was 56, 36, 15. Now we're going to add the 2330 because it was north of the celestial equator, right? That's what we found out in the analemma, 23.5 degrees north. So we're going to add that. This will come up to be 15 seconds, 66 minutes. Well, 66 minutes is 6 minutes more than 60. So that'd be 6 minutes, carry 1, and this would be 56 and 23 would be 79 plus 1 is 80. When you add those two together, you get 80 degrees, 6 minutes, and 15 seconds. That's the altitude of the sun above the celestial equator, above our southern horizon on the 21st of June. Does that make sense?
Okay, go over that one more time because I'm a little lost, so I'm trying to find you.
Okay. The celestial equator is 56 degrees, 36 minutes, and 15 seconds above our southern horizon. That's right. The angle from here to here. And you just told me from the analemma that on June 21st, the sun at noon is 23.5 degrees above the celestial equator. So above our southern horizon, you would add the 56, 36, 15 to the 2330, right? 23.5 degrees, 2330. Add those together. This adds the 15. That adds the 66, right? Well, that's more than a degree. So that's 1 degree in 6 minutes. So this would become 6 minutes. This was just 15 degrees seconds because we're adding anything to that. Okay, but this, you carried the 1 from here, and that gave you 9 and 1 is 10. 2 and 5 is 7, carry 1 is 8. So you're 80 degrees, and that's a degree symbol there. Okay, 80 degrees, 6 minutes, and 15 seconds above our southern horizon. Do you see that?
Not really. I keep going over it. I'll figure it out.
Okay. Well, here's the celestial equator, 56 degrees above our southern horizon. We figured that out over here. And then you just told me from the analemma that the sun on June 21st was 23.5 degrees above the celestial equator. So you add the 56, 36, 15 to 2330, and that's what we did here. Add those together, and that gives you 15 seconds, 6 minutes, because I added the 66, but 60 minutes is 1 degree, so carry a degree, and that would be 6 minutes, and then when you carried the degree, that would be 3 and 6 is 9, and that 1 you carried would be 10, carry 1 here, 1 and 5 is 6, and 2 is 8. So that's 80 degrees, 6 minutes, and 15 seconds. That's how high the sun is on June 21st. That means when you go out there at noon in a couple of weeks, exactly at noon, the sun's going to be almost overhead. It's not going to be exactly. It's going to be about 10 degrees south of overhead. Okay? Not going to be much, just a little bit. Right at 80 degrees. Okay? Can we move on? What was the next date?
October 15th.
October 15th. And what was the declination of the sun?
South.
It's what?
8 degrees south.
8 degrees south. So that was a little closer here. So this time we'll subtract 8 from our 56, and that would give us 48 degrees, 36 minutes, and 15 seconds. you subtract 8 from the 56, that gives you 48 degrees, 36 minutes, and 15 seconds. So it's just a little bit south of our celestial, a little bit south of where the celestial equator was. And the celestial equator is at 56:36. So in October, it's about half as high in the sky. Not quite, but close to it. Okay? Everybody fill in that one?
What was October again?
It's October the 8th, wasn't it?
October 15th.
October 15th, and it was 8 degrees south.
8 degrees south.
South.
Yes.
So you subtract 8 from the celestial equator, which is right here. Subtract 8 from 56, and you get 48, 36, 15. Did y'all get it? October 15th, 8 degrees south of the celestial equator. So that would be
Yes, sir.
48 degrees, 36 minutes, and 15 seconds. All right, and the last one was December 22nd or something around there.
Mm-hmm.
And this time we subtract the 23 because that was 23.5 degrees south. So that would be something about like that. So the 23.5 degrees south of this. So you subtract the 23.5 degrees from the 56. So this time, whoops, I can't get the eraser to work either. Let me try a right click. I thought a double click would work. It doesn't. Nothing's working. So you have to subtract, make this a subtraction here, and that would give you 33 degrees, 6 minutes, and 15 seconds. If you subtract the 23 from the 56, that gives you 33 degrees, 6 minutes, and 15 seconds. So that means on that day, the sun is just about a third of the way up in the sky. At noon, it's only about a third of the way up in the sky. 33 degrees, 6 minutes, and 15 seconds. All right. Now you better put on your jackets because we're going north to Altegard, Norway. Altegard, Norway is at, let's do it on the table first, okay, is at 70 degrees north. It's above the Arctic Circle, okay? Now, the declination of the sun is the same on these days wherever you are on the earth. But what we're asking for, what's the noon altitude of the sun at Altegard, Norway? So what we got to do is go back to our whiteboard, okay, and move everything, okay? So I can't erase a thing here, folks. Oh, maybe I can clear everything. Yes, I can. Okay. Now, what I'm going to try to do is move this box here. You can't see it, but it's in my way. I'm going to move it down here again. It's probably going to be in my way again, but I'll try to avoid it. Okay. And we'd have to draw everything all over again. Let's see if now I can draw my circle. No, I can't. Okay, so this would be awful if I try to do it. Here would be the globe. Oh, that's awful. Okay, there's the Earth. Okay, here you are in your heavy coat at Altegard, Norway. So you have a big heavy coat on here. And there's your head sticking out, but you got a hat on. So your zenith is directly overhead. Somewhere up there. Here is your celestial meridian. Oh, don't do that. Okay. Celestial meridian. The pen is going wherever it wants to. Okay. It goes up here. Whoa, I went way too far north. And down here. So here's north, there was south. Okay. Now you're at 70 degrees. So the equator is way down here. This is 70 degrees here. And here's the horizon. I wish I could draw a straight line, but I can't. So I'm going to do the best I can. Ooh, that's awful. Okay, that's your horizon. And 70 degrees is merely something like this. Okay, this is the 70 degrees here. So here's the celestial equator again. When you're at Altegard, Norway, the celestial equator is way down there. Okay, now let's go back to February. Oh, and by the way, what you have to figure out is how far above the celestial equator is, how far above your southern horizon, and this is your southern horizon here, is the celestial equator. Wasn't there a place for that, or was there? I don't know if there was or not. But it's only 20 degrees because this is 70 here. This is also 70, just like this is 70. So that leaves this to be 20 degrees. Right? That's how far the celestial equator is above the southern horizon when you're in Altegard, Norway. Okay, well, guess what, folks? What was that first date? February the 15th?
Yes.
And wasn't it 13 degrees below the celestial horizon, celestial equator? Am I remembering right? I didn't draw it well.
Yes, sir. 13 degrees.
13 degrees. This is 13 degrees. If you subtract 13 from 20, what do you have?
7.
7. So the sun at noon on February the 15th, that poor pitiful little sun there on Altegard, Norway, at noon is only 7 degrees above the horizon. That's just barely up there. Which means, of course, it probably didn't come up but maybe an hour ago, and it's going to set in about an hour. You know, you're going to have a very, very, very short day there in Altegard, Norway on February the 15th. Okay? Let's go up to June the 21st. Right? Was that the next one?
June 21st, yes, sir.
Okay, June 21st, the celestial, the sun was 23.5 degrees above the celestial equator. 23.5 degrees above the celestial equator. Okay, and the celestial equator was 20 degrees above the southern horizon. Add another 2330 to it, you get 43 degrees and 30 minutes. That's supposed to be minutes, not degrees. I don't think I can get my eraser to work, can I? No, I can't get the eraser. That's minutes. That's not degrees. Okay. So you add 20 degrees to 23.5, and you get 4330. That's as high as the sun gets. It doesn't even get halfway up. 43.5 degrees up is as high as it gets on the summer solstice. That's as high as it'll ever get. Okay?
So you said 2330.
2330, add it to 20, and you get 4330. Right?
Okay.
Okay? Then the next day is October 15th. And on October 15th, you're only 8 degrees below the southern horizon. So 8 degrees would be somewhere in here approximately. So rather than 13, it's going to be 8 degrees below the 20. And 8 from 20 is? 12. So on October the 15th, the sun is 12 degrees above the southern horizon. Okay, you may get 4 or 5 hours of sunlight that day. It's going to rise and only get about 12 degrees up and then start going down again. It's going to set 3 o'clock, 3 or 4 o'clock in the afternoon. It's going to be cold too, folks. Now, how about December the 22nd, was it?
Yes.
Okay. Where is the sun above the southern horizon of the celestial horizon that day?
23.5 degrees below.
Below. Where is that? In Altegard, Norway. The southern horizon is only 20 degrees. So you're below the southern horizon. In other words, the sun never rises at all on December 22nd. Probably not even on Christmas Day. Boy, wouldn't that be a bummer. Total darkness, or mostly darkness, all day long. Why? You're above the Arctic Circle. And on the Arctic Circle, anywhere above that, you're going to have at least one day of 24 hours of total darkness. Well, I say total. The sun doesn't rise, but it gets like dawn around noon. In other words, it acts like it's going to come up, but never makes it. So you start getting a little bit of dawn-like appearance shortly before 12 noon, and then it starts going like dusk shortly after noon. So it never comes up. Okay. So I think we finished that page, didn't we?
Yes.
All right. Okay. So you finished all the items on that page, right?
Yes.
All right. Now let's go down to the next page, and it's also crooked. Okay. Now I've got a problem here, and that Valerie's in the way again. Okay. Valerie, what is your problem? Okay.
I don't know.
What's that?
I don't know. I'm just a bad person.
Oh, I can understand that. Okay. You don't see it, but I'm moving you way to the other side. Also, Juan's there, and Roy's there, and Harry's there, but, Valerie's picture's there. And I'm there, too, but, of course, I'm not a bad person. Okay. All right. But that doesn't work either because that gets in the way of my cursor. Okay. Rip Van Winkle, this is number 6, awakens from his extended slumber. Do y'all know the story? Rip Van Winkle?
Vaguely.
Okay, I think he was supposed to sleep something like 70 years or something like that from his long extended slumber, and asked a passerby. I can't read it because
what year it is, so
yeah.
they can determine how long he slept.
Yeah. Okay.
Passerby quickly responded and then rapidly moved away.
Yeah, I would think anyone been sleeping that long is probably going to be pretty scary looking. Okay. Now, it was a 20-year. Okay, I'm sorry. But realizing that a 20-year snooze might be a world's record, he thinks he should pin down the date as well as the year. So he moves out from under that tree where he's been sleeping all that time, 20 years, and measures the altitude of the sun when it crosses his meridian. Now, how he knew that, I don't know, and how he had a constant sextant, I don't know, but he had it. He found that it was 44 degrees over his southern horizon. That was the altitude of the sun on this day of the year. Okay, so we got to go back to our board here. Okay, and we're going to erase all that ugliness. Oh, we'll erase, well, I don't know. I don't think we can erase parts of it. No. So let's erase it all. Okay. I've got to draw it again, though. Uh-oh, Scott's here. I think this may be Scott's first day here. Yeah. Scott, can you hear us yet? Scott, are you here? You are. Okay,
Yes.
good deal.
Just got on.
Okay. And do you go by Scott or Chris or Christopher or what?
Scott.
Scott. Okay, let me circle
Yes,
back.
sir.
Okay. Now, and since this is your first day, time out for a moment, folks. Let me just bring Scott up to speed. Okay. Here's where we've gone, where we've been, that kind of stuff. If you go to Blackboard, I'm sure you must have gotten there because you're there. Okay. When you go to the main page, I think it's called Content, okay, for this class, you'll see the syllabus is there. You'll see my locator card is there. When I'm in class, out of class, when I start work, when I end work, that kind of stuff. When I eat lunch, that kind of stuff is all there. There's, I can't say it in the right order. The research paper instructions are there. Please read those. The PowerPoints are all there. And somewhere down the list, you'll see PHS111 YouTube videos.
Yes,
And
sir.
okay, when you go to those YouTube videos and click on the link, you're going to see a whole list of them. The ones at the bottom of the list are the ones we've done this term, starting with syllabus and any of the ones below that. The ones at the top of the list are the ones that we did last term or sometime before. The reason I keep them in there is that every now and then something screws up and I can't record. Today I am recording, or most of it. We had a screw up early on and I had to lose about 20 minutes or so, but I got, we weren't doing anything new in class. So what you can do when you go to those YouTube videos, the ones from this term, the first one says syllabus. I go over everything about the syllabus, the research paper, the locator card. I go through the whole thing on Blackboard, and you'll see and hear everything I say. And then we got started in chapter 14. Okay?
Yes.
Then the next day's class, I don't remember. One day I don't think we could record because my computer ran out of memory, and that was just utterly ridiculous. Since then, I hope I fixed that, but that day I couldn't do a thing. So you'll have to go and look at last term's.
Last Monday, I think.
Yeah, okay. And then the next Wednesday, I think everything showed up. And I tried to go back over the first lab again on that Wednesday because it wouldn't record the Monday. So, and the lab is out there under messages. If you go to Blackboard messages, you'll see I've put 3 things out there so far. I'm soon going to put a 4th one. The first one was lab 1. The second was test 1. The third was lab 2. And the next thing I'll put will be test 2. Now, those are the things you fill in and you send back to me either by message or by email. I don't care which. Okay. And you can either take pictures or do a YouTube video, a PDF or however you want to do it. Scan it or take a picture. Okay. Now, I want to make sure I'm covering everything. If you go back to that first page, the content page, where it had YouTube videos and PowerPoints, all that. I also put several other files there. One is Space Objects in Perspective. It's a really interesting file. A student shared with me. I found it really nice, so I put it out there too. I have 10 pictures from the Hubble Space Telescope. Again, a student sent them to me. They're beautiful. I just put them out there. And somewhere down, the last one listed there is called a star map. It has some other part of the name. That star map is what you use to answer that first lab. Okay. Now, then the test is there, and you can use your book if you got a book, or the recordings, or whatever you can use to do the test. Now, the second lab is the one we're looking at now. So I'm going to back off just for your purpose so you can see it. And it's out there under messages, but it's a long lab. Okay? Okay.
When's it due?
Say again?
When's the second one due?
Oh, it's always at least a week after we do it in class, and we're doing it today, so it'll be at least a week from now. If you need more time, you can. I always give you a week for everything. Tests, labs, whatever. That always gives you 1 day to ask questions about it, and then it's due then. If you need more time, take more time, but get them in as soon as you can.
Yes, sir.
So this is like, what page would you say, 5 or 6 of this lab? I'm going to have to move a little bit here. Y'all can't see what I'm blocking. Okay. The lab begins way back up here with, can you see that? Motions of the sun?
Yes, sir.
Okay. You read that page. You don't have to send me anything on that page. Read that page. Read the second page. On the third page, you have a place with a blank. If you go back and listen to today's video, you'll hear exactly what you put there. Okay? All right. So there's that. Question number 2 at the bottom has a blank, but there's no question there. So you don't have to put anything there. They gave all the lead-in material, but they never asked a question. I don't have a clue what they were going to ask. Okay, you can read all this stuff, and that was what that second question was talking about, but they never asked a question, so I don't know what it was about. Now, the analemma, that is the biggie. That is the most important thing in this lab. And go back and listen to the first part of this, and I'll explain as much as I did to them. You'll hear me do it all over again. And using that analemma, we're going to fill in the rest of it. This page, again, is reading, and these turn sideways. I don't know why. I held my iPad the same way over the same thing. And then we filled in question 3. I'll get back to it in a minute. Okay, pick up your finger. Okay, we filled in question 3. And 4 had 2 parts, one you answer here and one you answer down here. And then we filled the table next, and we just finished doing that a short while ago. And let me move you out of the way because you're in the way again. Okay, move up here. And we filled in that table next. Okay? And you'll have to listen to the video and see what happened. Now we're moving to this table. We've got Rip Van Winkle just waking up, and he pulls out a section where you just happen to have with him, finds out that exactly when the sun crosses his local meridian that day, he finds it's at 44 degrees above the southern horizon. And we were going to the whiteboard to draw that in, and that's where you came in. So let me go back to the whiteboard, and I hadn't had anything drawn yet. So I'm going to start kind of backwards from what we did before, and there Harry's in the way again. So I'm going to move Harry over here to the side. Okay, try to get him out of the way. Okay, I'm going to move this thing as far as I can here. Y'all can't see what I'm moving, but it's things that are blocking my drawing. And my drawing is really important, as everyone will tell you. Now, I'm having to do this freehand because the system screwed up. So here's your local meridian. It goes from due south through your zenith, which is directly overhead, all the way down to due north. And that's supposed to be one single arc, one smooth single arc. Laugh all you want to, but okay. And here's old Rip Van Winkle down here standing on the globe somewhere here. And I don't draw globes very well, but let's just imagine that's the globe. And he's standing here, and he's in his long white beard because he's been sleeping for 20 years. And he was outside the whole time, so he has a long old beard. Never mind, I'm just being stupid. Okay, so here's his horizon here. That's supposed to be a straight horizontal line. It's nowhere close. Okay. If my pens were working, that would do. Here's the zenith directly overhead. Okay, there's the zenith. Now, we found out that the sun at noon on the day he awakens is 44 degrees above the southern horizon. Again, here was the southern horizon here. The northern horizon's over on that side. We're not going to use that. So this is 44 degrees here. Okay, and that's the sun at noon on whatever day he awoke. And that's what he's trying to figure out, what day he awoke. And that's at noon. That's how high it is. So let's go back to our lab, and let's see what else we know. Guess what? Valerie's in the way again. Goodness gracious.
Sorry.
What is your problem, huh? Okay. Yeah, it's probably still in the way. Okay, so let's see if we can figure it out from here.
He knows that the latitude of his chosen spot on the Hudson River in New York is 42 degrees.
Okay, that's his latitude, is 42 degrees. Okay? Now, so let's go back to our drawing and get that in there. Okay? His latitude, that's how far he is above the equator, is 42 degrees. So this is 42 degrees here. That means the celestial equator is 42 degrees below his zenith, right? So this is 42 degrees. That corresponds to latitude. That puts the celestial equator right here. Because you see, on the surface of the Earth, his latitude is how he is above the equator. So his zenith is how far he is above the celestial equator, 42 degrees. Okay. Now, this total angle here from his zenith to the southern horizon has to be 90 degrees. And here's 42, there's 44, so that adds up to 86 degrees. How many degrees do we have in here? This is 42 and that's 44. Say again? 4 degrees, you're absolutely right. So the sun at noon is 4 degrees south of the celestial equator. Okay. 4 degrees south of the celestial equator. Let's head back down to here and head back up to our analemma. Here we go. Now what do we say? 4 degrees south of the celestial equator? That means on the day he awoke, the sun was here. Now that is early October. That looks to me about October the 4th because there's October the 5th, right? So he either woke up on October the 4th or he woke up on March. Looks like maybe the 11th. Would you guess? I think that's the 10th. That would be the 11th. So he woke up either on, what did we say? October 4th or March 11th. Okay? So I think that answers that next question. Okay? Now, Juan is in the way again. Juan, can't you stay out of the way here? Okay.
That was January 10th?
No, it wasn't January.
October 4th or March the 11th.
Yeah, October 4th or March the 11th. We'll go back and look at that. Okay.
Which one?
Those are on what 2 possible dates could he have awakened? So down here, the first answer is either, what did you say? October 4th
or March the 11th.
Or March the 11th. Now, whereas your question is how we got that?
No, I see it. I was looking at the wrong thing.
Okay, you got it now? Okay, good deal. Okay. Now, those are the 2 possible dates he awoke. He notices the buds are just appearing on the tree that he slept under. So guess what day it was? Would the buds be sure? Yeah, March 11th. Okay, so you've answered that. The first answer here would be either October 4th or March the 11th, and the second answer was March the 11th. Okay. Now, here we need to read this, and it's going to be sort of hard going here. And of course, 1's in the way again. Goodness gracious, 1, what's your problem? Okay, here we go. It's still in the way, sorry. I think I'll move them over here this time. We're through with Rip Van Winkle, so I'm going. Y'all don't know what I'm moving, but it's the track that has your pictures or names on them. That's why I'm calling out names. Okay, here's what we got. As we saw previously, the analemma graphs the daily difference between clock noon and apparent noon when the sun crosses the meridian. As an example, check the analemma, and they put the wrong thing. It's 48.1 or something like that. They had it 4.3. I don't know how they got that. To see that on October 15th, the sun will cross the meridian 4 minutes before clock noon. So remember this, October 15th, 14 minutes before clock noon. So let's go up here to the analemma, October 15th. There's October 15th. And sure enough, if you go up the scale here, up the scale here, up the scale here, yuck, I'm not going to be able to reach the top. Y'all see the line that I was on? That's the fourth one in from the edge. Okay, sure enough, there it is, 14 minutes, and what did it say? Ahead of clock noon, right? Before clock noon. So anything to the left is before noon, anything to the right is after noon. Got it? To the left is before clock noon, to the right is after clock noon. So let's go back to where we were. Okay. On October 15th, the sun will cross the meridian 14 minutes before clock noon. Okay. Now there's a blank there, but there's nothing that you have to put in there. Here is the next question, I think. Number 7. For the dates given in the table below, use the analemma in figure 48.3. They got it right this time, or 48 whatever. I think it's 48.1. To determine whether, okay, now the first blank here is what you're going to put in this column is before or after. Don't put anything else, just the two words, before or after. That's all that goes in here. And then we'll say the amount of time in this column, okay? And on these dates, determine whether it crosses before or after clock noon, and then the last column by how many minutes, okay? So here are our dates, and somebody write them down again. Okay, January 10th.
I got them.
February 15th, April 15th. You got them, okay? So let's go to the analemma and look those up. We're going to trust Valerie to call out the right dates so y'all won't be getting them wrong, and she's the only one that gets them right. No, she wouldn't do that. Okay.
Right.
Okay. Give me the first date.
January the 10th.
January 10th. This appears to be January 10th right there, and you'll have to go all the way up this line. And I'm not going to make it because I'm going to run out of thing. What is it above this line? Oh, wait. The question is, the first question, before or after? Before or after?
After.
After. Okay, so the first blank is after. Then you go up this line. And y'all will have to remember which one that is. It's 1, 2, 3, 4, 5, 6, 7 from there. So let's see if I can remember that. Okay. I'm thinking that's about 7 minutes. Is that what y'all got? Valerie, have you printed yours off? Did you get that to be about? I
printed mine off. Yes, I did.
Did you get about 7 minutes?
It's better for me to look on the computer. I can't see it on my printout.
I think that's 7 minutes. We'll just go with that. Okay, you see how I got it?
Yes.
You follow this line down. The thing is, I can't show it on the computer, but follow that line down, And remember, okay, each line is 1 minute, right? So let's go all the way down here to January the what? What date was that again?
January 10th.
January 10th. There's January 10th. Get out of the way. Okay, January 10th. So let's count over. 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes, 7 minutes. That looks like it to me. What's the next date?
February the 15th.
February 15th. Here we are. Before or after?
After.
After. And I think if my memory right, this was 16 minutes here, so that's about 14 minutes. Is that what you got?
That would be correct.
Okay, 2 from the right hand end would be 14 minutes. Okay, what's the next date?
April 15th.
April 15th. Okay, we got to move up into springtime here. Oh, here we go. I see April 15th, or I get close to it. Okay. I think that's April 15th right there. You see, that's the 15th, and that's it. Are you before or after?
You're still out.
Just barely after. I would say a few seconds after, not even a minute. So the first column is after, the second column, a few seconds. That's all I would say. What's the next date?
July 30th.
July 30th.
Our clock time is 1 minute.
I think it's less than a minute on July.
On
April the 15th. That's tax. It used to be tax day. It wasn't this year. April 15th. You're just almost at clock noon. You're just a little bit after, and I'd say just probably 15 seconds or something like that. Maybe 20 seconds after clock noon. Just a few seconds after clock noon. Okay. The next was what? July something?
July 30th.
July 30th. There we are at July 30th right there. What seems to be, are we before or after?
We're before.
Here's July 30th.
After.
After. And I would say, you make a guess, 6 or 7 minutes, something like that. You choose. 6 or 7 minutes after clock noon. July 30th. What's the next one?
September 1st.
September 1st. Goodness, we got to go way down south again. Whoa, no we don't. September 1st. Wait, oh, I had it on the screen. I moved it. Okay, here's September, right here. Here's the 1st, there's the 5th, the 4th, the 3rd, the 2nd, the 1st. Somewhere right in there, I think. So it's just barely after, and again, I'd say maybe 30 seconds or something like that. Wouldn't you?
Yes.
Okay. What's the next one?
The last one, October 30th.
October 30th. This one we have to go downhill. Okay, remember every line is a minute, so we're going to count back. And the last one over here is 18 minutes. So we'll count backwards from 18. October 30th. Whoa, look at us there. Okay, October 30th. Before or after?
Before.
We finally got a before, okay? It's raining like crazy here. I don't know if it is where you live, but we just picked up a rain. And that looks like 2 minutes from there. What was that? That was it 16 minutes? Is that what you said, 16?
18, I think.
Okay, the far right is 18. Far left is 18. This is 2 minutes over. So that would be right around 16, wouldn't it?
As far as I can tell, it looks like 16 to me.
Yeah, looks like 16. All right, good deal. So I think we finished that table, didn't we?
Yes, sir.
All right. This is just going right along, isn't it? Okay, let's go back here. And
Last one.
last page, oh, the one we've been dreading forever. Okay. And of course, guess what? This block of people are in the way. Roy, what are you doing in the way again? Okay, I'm going to move you way down here somewhere. Okay. Let's see if I can read what the page says. Okay, number 8. Determine the altitude over the southern horizon for the actual sun and the time when it crosses
Your local
meridian on the dates in the table below. So we're going to have to go back to the drawing board and do these dates. You got them down: May 15th, June 15th, November 4th, and December 25th. Okay? And we're going to first determine the altitude of the sun. And to get that, we're going to have to do what we did before. And at least, Scott, this will be, I'll just fill you in on this a little bit. How we get this, the altitude of the sun, and then we'll do the time. Okay?
All
so,
right.
Let's go back to our drawing board. Now here it's done it again. For some reason, I've lost my screen. I don't know where it went. Okay. How did I get it back last time? I think I may have hit an escape. No, that didn't work.
So are we using our Bessemer campus?
Yeah, we'll use all that kind of stuff. So let's just do it from memory. Okay.
It was 33 degrees latitude.
23 minutes
23
and 45
minutes,
seconds.
45 seconds.
Okay. Now that's the latitude. So you subtract that from 90, and we got the 56 degrees, 36 minutes, and 15 seconds, right?
Right.
That's the altitude of the celestial meridian from Bessemer, right? That's our local meridian. We're using Bessemer. Okay. Now, from there, we look at the analemma and found out, because there's the celestial equator right there at 56 degrees, 36 minutes, and 15 seconds. Okay? Now, let's go to the analemma, and it's date of May 15th. Ooh, I went past it too fast. May 15th. Okay. God, this is too sensitive. Okay, let me use the arrow. Do it more slowly. Okay, May 15th. There it is, May 15th. Okay. On May 15th, the sun is at what declination? See my cursor? 19 degrees north of celestial equator. So if you add 19 to that 56, 36, 23, okay, add 19 to, oh, no, not that. Clear, okay. 19 plus 56, that's about 75 degrees, 36 minutes, and 15 seconds, right?
Uh-huh.
So that's the, isn't that what it asked for? The noon altitude of the sun on the 15th of May, right?
Right.
Does everybody agree? 75 degrees, 36 minutes, 15 seconds. Okay, while we're here, what's the next column asked for? What time does it cross the meridian? Is that it?
Right.
Okay, well, let's see. It looks like it's 4 minutes. Which side? Before or after? Before clock noon, and 4 minutes before clock noon would be 11:56, wouldn't it? So that's what we put in the last column. On May 15th, it was 75 degrees, 36 minutes, and 15 seconds was the altitude of the sun above the southern horizon, and the time was 11:56. Everybody see that? All right, what's the next date?
June 15th.
June 15th. Oh my goodness, look at June 15th. First, what's the declination of the sun on June 15th? Right around 23 degrees. Okay, north of 56. So 23 plus 56 is 79 degrees, 36 minutes, and 15 seconds. So that's the noon altitude of the sun on June 15th. At what time does it cross your meridian?
At noon.
At noon. I mean, it's sitting right on the line. That's not even a couple seconds. It's at noon. Okay, good deal. All right, that was the second date. What's the third date?
November the 4th.
Oh my, we got to go way down south here, don't we? November the 4th. It's going to be over here on the left. There's November. I think the 4th is right about here. Okay, what is the declination of the sun on that day?
15 degrees.
15 degrees south. So we take our 56 and subtract 15 degrees from it. And that's 41 degrees, 36 minutes, and 15 seconds. Right?
Okay, I got you.
Everybody got it?
Yes.
All right. Now the question is, and what was the date again? 4th of November?
November. Uh-huh.
Okay.
Yes, sir.
So we're going to have to go up.
Degrees.
Say again?
41 degrees.
Yeah. Okay. No, not degrees.
Yes, it's 41 degrees. That's correct.
Oh yeah. Oh yeah. When you subtracted 15 degrees from 56, you got 41 degrees, 36 minutes, and 15 seconds. Right? All right. Now the question is, what time of day does the sun cross the local meridian? And if my memory's right, the last column here was 18 minutes, wasn't it? And that would have been 17. You can call that 16, 16 and a half, what I'd say 16. 16 minutes. Which side of clock noon? Before. So that would be about 11:44, wouldn't it? AM. What does AM stand for? Anti-meridian, which means before noon, before it crosses your meridian. Okay. Now, was that the last one? Or is there one
December
more?
25th.
Is what?
December the 25th.
December. Oh, Christmas Day. Who brought me a present? Nobody. Okay. Oh, look at December 25th. Okay. First, what do you think the declination of the sun is that day?
12. Wow.
No. Declination of the sun?
Degrees.
About 23 and a half degrees. It's almost right smack on as far as it gets. Okay. Remember that 8 is pretty flat there, so it's awfully close. So about 23 and a half degrees below the celestial celestial equator. So if you subtract 23 from 56, you get 33 degrees, but then you also subtract 30 from 36, 6 minutes. So 33 degrees, 6 minutes and 15 seconds. That's the altitude of the sun above the southern horizon. Did everybody get that? 33 degrees, 6 minutes, and 15 seconds. You subtract the 33 from the 56. I mean, you're 23 from the 56 and get 33. Subtract 30 from the 36 and you get 6 in 15 seconds. And what time? Noon, yeah. Maybe 5 or 6 seconds before noon or something like that. Let's call it 12 o'clock noon. That's good enough. Is that it? We're going to end on Christmas Day?
That's it.
Okay. I'm sorry I cheated you out of 2 minutes of your tuition dollars. I feel so bad. But guess what? There'll be no refund. Okay. So you're just going to have to live with it. Any questions on the lab? Okay. Now, I've got a few things to do once we end the recording today. But once I do that, then I'm going to be loading the second test for Chapter 15. And it'll be out there sometime this evening. I don't know what time.
I have 2 questions.
Okay, what's the questions?
What was the time for November 4th?
November 4th. It was about 16 minutes before clock noon, so that'd be 11:44, wouldn't it?
Yes.
Okay. And what was the next question?
Number 6. There was 2 parts to that question.
Okay. I think I remember which one that was, but let's go see. Number 6. That's further down, I believe.
On October 4th or March 11th.
Yeah. Okay.
That was March 11th.
And then March the 11th was the second part. The first part was what?
Got you.
Okay.
Okay. I thought I missed something. Okay.
Well, I'll surprise you if you did. Okay, never mind. Okay. Any other questions? Great questions. See, he wanted his full tuition dollar and he got it, didn't he? Okay.
You are right.
Are there any other questions? All right. So next time we will pick up where we left off in Chapter 16. And I have a feeling it's going to be a long one next time. We'll probably have lecture just about the whole time. And probably go on and start in 17. And then turn around the next time and have the lab. Actually, if we finish 16 in time, we may have time to do the lab. Because guess what? The next lab is going to be one that you do a lot of it on your own. And it's going to be, I hope you find it interesting, but we'll talk about that next time. If we don't have time, we'll do it next Monday. And we'll get it done then. All right. Any questions? All right. I've got to figure out how to end Zoom because I can't find Zoom on the board anymore. But anyway, y'all have a good 2 days. We'll see you on Wednesday, okay?
See you Wednesday.
All right.
Thank you.
So I'm going to shut things down here and try to find Zoom to end the session. There, I think I've got it close anyway. Yep, I've got it. Any questions before I shut it down? All right. Take care. See you on Wednesday. Yes.
Mr. Fowler.
Yes.
If I haven't got it printed off, but I got like everything you said on here, like could I like write that on a piece of paper and email it to you, or like do you want it like in the format of the lab?
No, if you write it down and send it to me, just make sure you got everything covered because I'll be grading from the template of the lab. So
yes,
don't skip anything. Okay. So yeah, you can go back and look at the lab, or can you do? Yeah, you can do that. You can't do it on your computer, but you can do it on your phone. So make sure you got everything filled in. That'll work.
Yes, sir, I will.
Okay, good deal. Any other questions? Great question, by the way. Okay, Scott, you feel like you're up to speed?
Yes, sir.
Okay, good deal. It's good to have you in class.
All right, thank you.
All right. All right, I'm going to end the meeting then. Take care.
All right. So one more question.
Oh, yeah, right.
So we're starting. We just are we starting at 2:30?
Yes.
Here every Monday and Tuesday.
We start 2:30 and go pretty much until 6:15 most days. Some of the days, some of the labs may be shorter than others, so we might end a little before 6:15. But most of the time, it's 2:30 till 6:15.
Yes, sir. Okay.
It's 2 hours and
All right.
15 minutes of class and an hour and a half of lab. But some days we'll have more class and less lab. Other days we'll have less class and more lab.
On the test, so it's ready to take and just send it. The first test.
Say that one more time.
The first test is ready to take.
Yeah, you can take it. It's out there. And the second test I'll be posting sometime later today.
Okay.
All right. And did you catch anything? That's the big question.
Sir?
Did you catch anything?
A little bit, yeah. I've been through chapter 14.
Oh, no. I meant fishing. You went fly fishing, didn't you?
Oh, yeah.
All right. Yeah, I ask you important questions here.
Yeah, well, sort of. The guy, I took my little nephew and they
Right.
went biting. We was fishing wild trout
Uh-huh.
on private land, and they're really big. We got a lot of bites. Didn't hook anything.
Mostly
guy hooked
mosquito
one.
bites, huh?
Yeah, a guy hooked one and let me reel it in, a big rainbow trout.
Oh, wow.
My nephew caught a big largemouth bass the next day.
Nice. Yeah.
We just went fishing by ourselves, so he was really happy.
Yeah, that made his trip for him, I bet.
That made it worth it. Yes, sir.
All right. Well, good to have you back.
Okay, thanks.
Uh-huh. Any other questions?
I don't have any.
Okay. Take care, folks. We'll see you Wednesday.
Yes, sir.